speaker, Professor Tessé. The title of his lecture, Pseudo-parabolic regularization of forward-backward parabolic equation.
Good morning. It's a great pleasure to be here again in Moscow and to participate again in this very long and successful series of conferences. And I would like to thank the organizing committee and particularly Professor Skubaszewski for giving me this opportunity. So my talk today is this one which is displayed, and our interest is about this problem. And this is a quasi-linear parabolic equation, and the main feature of the problem is that this first function, this response function here, is non-monotonic. So if this second term were absent, then the problem would be ill-posed, since it would be a forward-backward parabolic equation. Now, the reason to add this second term is, in fact, that this gives rise to a specific regularization of the equation and of the associated initial boundary value problems. And in fact, our concern is about investigating the properties of this family of problems with different choices, either of the response function or of the regularizing term. And the main feature of this term is that instead it is steadily increasing, and it goes to some bounded values at infinity. And because of this property, the problem is degenerate pseudo-parabolic, since psi prime, of course, vanishes at infinity. And what the results I want to discuss have been obtained jointly in 3 papers, in a series of papers, with Michiel Birch and Flavia Smarrazzo, my co-workers in Rome. And in fact, these are the references, and these are the first 3 papers I will talk about if time permits. And these other 2 papers came before, and they address the same problem under some more restrictive assumptions on the initial data. Now, in this equation, as I was saying, there are essentially 2 functions which play a very important role. And as for the response function phi, we are particularly interested in this shape. Sorry, this of course would have to be small phi. The main property of this function is that it vanishes at infinity, and of course it is non-monotonic. This kind of functions is suggested by many important problems, for instance, image processing, and that is why this type of nonlinearities are called of Perona-Malik type, going back to the original paper of by Perona and Malik in image processing. But curiously enough, exactly the same time of nonlinearities arises in other interesting problems like population dynamics or independently in oceanography problems. So there are several good reasons to address this kind of problems. And speaking of forward-backward equations, apart from the regularization, they are mainly of 2 types. In one type of model, the dependence is on the space gradient of the solution, and this is what happens, for instance, in image processing or in oceanography, whereas in another kind of models, the unknown is the U itself, And this is what happens, for instance, in population dynamic models or in phase transitions. The main feature, of course, is that these functions are non-monotonic, so that the diffusion is forward where phi prime is positive, and these are called stable phases, but the diffusion is backward where phi prime is negative, and these are unstable phases in the parlance of phase transitions. But of course, since these values depend on the solution itself, which is unknown, you do not know a priori how to treat this problem, which is inherently ill-posed. Now, it's a remarkable feature, a well-known one, of course, is that in one space dimension, there is an obvious link between these two models, since in one space dimension, the first equation is nothing but this one. And formally, if you differentiate with respect to x this first equation, and you set u equals z x, then you get exactly the second equation. So this is an obvious link, but it has been exploited in many cases. Now, because of these features, the corresponding initial boundary value problems are ill-posed, and regularization is needed. So going back to our equation, this one, this short discussion tells us that, in fact, this is a regularized version of a forward-backward equation. So our attention is drawn to regularizations, and several different regularization of the same equation has been proposed. One very important, which has been used many times, is the so-called pseudo-parabolic or Sobolev equation, where you just add this term. And this has been used in several papers in the early 90s of the last century. For instance, there is an interesting paper by Novikov and Pego, and there is a series of seminal papers by Plotnikov, very interesting ones. Later on, there is another kind of regularization, and this is exactly the one we're interested today. And the main difference with respect to the first one is that it is pseudo-parabolic like the first one, but it degenerates at infinity, since this psi prime goes to 0 when u is very big, when u is large. And this has been proposed in another very interesting paper by Barenblatt, Birch, Dal Passo, and Dughi, and I will try and explain why this regularization has been proposed and what are the main differences of this kind of approach with respect to the Sobolev regularization. A third type of regularization is completely different, and it is the so-called Cahn-Hilliard regularization, where instead of this term, you add this square Laplacian term. And of course, all of this regularization derive from different modeling arguments which have been proposed to restore well-posedness of this problem. And even this kind of regularization has been studied by Plotnikov and by Bellettini and co-authors in a series of papers. But generally speaking, much less is known about the Cahn-Hilliard regularization and its properties with respect to this other kind of regularization. And then there is, I would just to mention for completeness, there are completely different approaches which in fact are based on the idea of a time discretization or sometimes a space discretization. These kind of regularizations are more suggested more by numerics, I would say, with respect to these kinds which are suggested by modeling arguments. And the advantage, for instance, of time discretization is that to some extent it reduces to a problem to a quasi-stationary model, so that you can make use of variational arguments like those used particularly by Tinderler and De Mulini and other authors. And then, of course, there is a very wide literature concerning possible modification of this equation without any regularization, but possible modification so that you obtain a well-posed problem. But okay, to some extent, it's a matter of taste of the authors. So I would like to motivate and to explain how this regularization arises, since we will focus in particular on this second regularization, which is very interesting. As I was saying, this was proposed by Barenblatt in that joint paper of his with Birch, Dal Passo, and Dudi. It is a 91 SI Journal Mathematical Analysis. Here the main idea is that the problem is ill-posed since you do not keep track of a very important time delay effect. If you do that, if you include this time delay effect, the true equation, in some sense, should be this one, where this in the original model, this K0 has a meaning of diffusivity. And if you start from this model, where this K0 is the ratio of the previous function phi of u through u, and you make a formal development with respect to this relaxation time, then what you get is exactly the equation we want to study today, where there is a relation, of course, between psi and phi, and the relation is this one. So, for instance, in the model case where phi of u is of this kind, then psi of u is this one, and as you see, it goes to plus and minus pi over 2 as u goes to plus and minus infinity. And then this is the reason why the regularization is indeed pseudo-parabolic, but it is degenerate pseudo-parabolic. So this feature is completely different with respect to the case of the Sobolev regularization, which formally corresponds to the choice psi of u equals to u, and the fact that this regularization vanishes for large values of u gives rise to a more realistic model with respect to this one. In what sense? Well, this regularization is very weak when u is very large, and so this allows the fact, very important qualitative fact, that this equation gives rise to the formation of singularities, while this is impossible for this equation. What do I mean by formation of singularities? Well, the main feature I have in mind is that for this equation, if you start from an initial data which is a function, even a very regular function, then in finite time, for positive times, you will have in the solution, for instance, a Dirac measure, or more generally, some Radon measure. And this is why it is important to study this kind of equation. The natural space where to study will be a space of function of time taking values in a space of Radon measures, which is an important novelty with respect to the existing literature, but it is completely natural for this kind of equations. Now, there are many open problems about this family of problems. One first problem, which I want to address in particular today, when you take the limit when epsilon goes to 0 of the model, which I call the vanishing viscosity limit by analogy with the case of hyperbolic conservation laws, when you do that, expectedly, the solution you will obtain will depend on the regularization itself. That's, of course, from the conceptual viewpoint, an important point to address. So the question is how the solution you obtain of the regularized problem, how does it depend on the choice of the regularization? This is important in the sense that you have to, it's important to stress the fact that modeling itself, to some extent, should suggest the right regularization, since from the mathematical viewpoint, you can make many different choices. But if you want properties which are in agreement with the physics you are trying to describe, then the regularization should be chosen properly according to the physics to a certain, in some sense. Another important problem, here I refer to the 3 papers I mentioned before with Birch and Smarrazzo, is the fact that when you have this degenerate pseudo-parabolic regularization, you will see that singularities can develop, so there is a need of what I could call a deregularization theory, namely to describe as completely as possible which kind of initial data will have the properties of generalizing these singularities, which not. Another problem, this is also very interesting, if you want to make a complete description on this point, then you realize that this is linked by a formal time reversal transformation to address the regularization theory for this kind of equation, where this chi now is monotone, but nevertheless this is a quasi-linear parabolic equation, and you can define random measure-valued solutions for this kind of problems, and even for this kind of problems there is no good regularization theory. What do I mean here? Suppose you define a solution of this family where initial data is a random measure. What will happen for positive times? Will it keep being a random measure, or will it become a function-valued solution? If it does, this is a kind of regularization, of course. This is another different topic, but very much related to this one, which is worth addressing. And then, of course, there are many other problems which can be addressed. Another important point is that even if you do choose a specific regularization, then differently from the case of hyperbolic conservation laws, you do not have a general uniqueness result. So what do I mean here? For hyperbolic conservation laws, if you introduce a viscosity term, then it is well known that in the limit, the viscosity solution you obtain is also an entropy solution. And for entropy solutions of the problem, the famous Khrushchev theorem tells you a priori that you have a uniqueness result. So you have jointly well-posedness class for this problem, since you have a general uniqueness result. Unfortunately, no general uniqueness result is known for this family of problems, even for the Sobolev regularization case, for instance. So the theory is not so advanced, not so satisfactory as this one in that general respect. That's another very important open problem. And then, of course, you can address qualitative properties of solutions, for instance, asymptotics for large times. And then, of course, another topic which would deserve much, would be worth investigating, would be numerics for this kind of problems, which is very important for applications. Now, to describe the kind of difficulties of this family of problems, it is important, it is informative to go back to the situation in the case of phase transitions, where the same problems are studied under different assumptions on the function phi. The function phi, which naturally arises in phase transitions, is of cubic type, something like this. So the behavior at infinity is completely different from the case of phi of Perona-Malik, which is much more difficult and which is the one we want to address today. Let me go back, sorry. Okay, this is the phi we want to address, and this is very, as you see, this goes to 0 to infinity. Much more is known in the case of phi of cubic type, which has been studied in the framework of phase transitions. Okay, for what happens in this case? What happens in this case, I will try and summarize. There is a series of at least three papers by Plotnikov related to this problem. The problem you want to study is this one. This is an ill-post problem, okay? And suppose you start in L infinity, which is a very natural choice since you want this quantity to be bounded. Now, what Plotnikov did was to use the Sobolev regularization. So formally, you substitute, you replace this problem by this one, where this V is the chemical potential, which is the sum of phi of u plus epsilon ut. So if you replace this expression here, you obtain exactly the Sobolev regularization of this ill-post problem. And then for every epsilon, it's easily seen that there is a unique strong solution of this problem, of the regularized problem. The reason is that this is a pseudo-parabolic problem, so it is very easily treated. It amounts to replace the Laplacian by its Yoshida approximant, nothing else. So this is essentially an OD in a Banach space, so this is very easy. And then the problem is to send epsilon to 0. And now what happens is that you can get rather easily estimates of the family of solution U epsilon and of the related chemical potential in L infinity of the cylinder and of the chemical potential in this other space. And these estimates are uniform with respect to this viscosity parameter, say. Because of these estimates, you have a compactness in the proper sense of these families, so that you can get easily, letting epsilon to 0, this relationship between the limiting values of this family, say u and v. You see, u will be some limit or the limit of some subsequence of this family in this space, and you will get this relationship very easily. How? Well, you go back to this regularized problem, you write the equation in weak form, and then the compactness you have is enough to get this result. Of course, this is not satisfactory since there is no link a priori between the limiting values u and v, but this was the main contribution of Plotnikov. He was, in that paper, he was able to characterize the limiting Young measures associated with these families, which are uniformly bounded. And what is very interesting is that the limiting Young measure associated to U is nothing but a superposition of three delta functions, and these three delta functions are concentrated on the branches of this cubic. Namely, essentially, what you do is to fix V, and you look at the roots of the equation phi of u equal to v. Of course, you have three roots since this is a cubic. And the limiting Young measure associated with u is the superposition of three delta measures which are supported by these three values, C1, C0, and C2. If you plug this information if you use this information, you get this relationship between the limiting value u and the value of v. So u is a superposition of these three phases, okay? And this allows you to say that this couple is a solution of the problem in the sense of Young measure. And again, if phi were monotonic, you would get the usual notion of which solution. So this is the situation for the qubit, which is very neat. You have a very good existence theorem. Of course, you do not have uniqueness, unfortunately, but that's an open problem. How do you get this uniform estimate? In particular, a major tool for this analysis was this estimate in L infinity of the family U epsilon. The main tool was this one. And this follows from the existence of positively invariant regions. This was already observed by Novi-Cohen and Pego. And this depends on the property, on these properties of the function phi, okay? Suppose that phi has these properties and that the interval u1, u2 satisfies this inequality. Then if the initial data u0 take values in that interval, then you will get that the solution takes values in the same interval for every positive time. And this, of course, that property is certainly satisfied if you take u1 sufficiently small and u2 sufficiently large. And this depends, of course, on the shape of phi, which is a qubit, you see. That property is absolutely trivial. If you take u1 sufficiently small and u2 sufficiently large, then it is certainly satisfied. Okay, the same argument in principle could apply also if phi is Perron-Malik, but unfortunately in that case this property, the property 4, is satisfied only if you take u1 and u2 in the increasing branch, which of course is trivial, since in that case you do not notice at all that the problem is ill-posed. So you are only dealing with the stable case, which is not the interesting case. So this approach is absolutely useless in the case of Perron-Malik type. And there is a reason for that, of course. The reason is that L infinity estimate would not be suitable for this kind of problem. They are not adapted to this kind of problem. Now, fortunately, it turns out that for phi of Perron-Malik type, the whole positive half-line is invariant for solutions. And the way to prove this is exactly the same way used by Novi-Cohen and Pego to prove a property 4, namely you take advantage of a family of entropy inequalities which are satisfied by every solution of the problem. So if you do that, and if you take advantage of this remark, you can argue as follows. Okay, L infinity estimates are too much, but anyway, we do have a conservation of mass. Now, suppose we start from a positive initial data. Since the positive half-line is invariant for solutions, the solution will be positive for every positive time, so that this conservation of mass, which is just this equality, becomes an equality in L1 of omega for every positive time, and this gives you then an estimate of U epsilon at least in L infinity 0t values L1 omega, since this quantity is equal to the total mass, to the L1 norm of the initial data. Okay? Of course, this is enough. Since this family now is uniformly bounded in L1, and since L1 is a Whittle star compactly embedded in the space of measures, of finite random measures, this is enough to tell you that in the limit you can suppose to have some subsequence which converges to a random measure. But you can be more precise if you use this biting lemma. And then you can say that there is some sequence U epsilon j, some sequence of subdomains of the cylinder which this property. You can split the sequence in the sum of two terms. And this is the characteristic function of the complementary set of A and J. This sequence is uniformly integrable so that it is weakly compact in L1Q by Vitalis' theorem. This remaining sequence will converge to some random measure. This is the biting lemma. And so the conclusion is that in this case, relying on that L1 uniform estimate, what you expect to obtain in the limit is this relationship between U and V. This is the regular part of the limiting measure, and this is the singular part. Now, if you compare what you get, which is this quality, with what we had in the case of a cubic type, which was this equality here, you see that the structure is the same, but here U was a function L infinity of the cylinder, whereas here we have, or at least we could have, a function of time which takes values in the space of random measures. And this is the singular part, singular with respect to the Lebesgue measure. Now, of course, this is only one possibility in the sense that your limiting value, a principle, it takes values in the space of random measures. But nothing forbids a priori that in fact it is more regular, so that you could argue that, okay, this is a general argument, but maybe this term never applies, so our solutions are function valued, and there is no actual need to study functions of time which take values which are random measures. So this is just what I was saying. This procedure suggests that you could have solutions which take values in the space of random measures for positive times, so that you would have the regularizing property, the regularizing properties of the problem in the limit when epsilon goes to 0. Please recall that here we were using we were using the Sobolev regularization, which is not the generated infinity. There is a very strong argument which supports the fact that, in fact, singular term appears in the solution, and not only in the limit when epsilon goes to 0, but even for positive epsilon, if you make use, instead of this Sobolev regularization, which is very strong, if you make use of the pseudo-parabolic degenerate regularization, which was suggested by Barenblatt, since this is the generated infinity. And in fact, there was a nice example, a nice remark in this paper, which was dealing with this equation depending on the gradient, on the space derivative, in one space dimension. And the space where they were working was the space of bounded BV functions, okay? And this is exactly the time of phi and the time of psi which we are dealing with today. Now, what they gave an explicit example where even if the initial data is very regular or even C infinity, the solution for positive time becomes discontinuous with respect to x, okay? So there is a dramatic loss of regularity. And by the transformation I was discussing at the beginning, if you think of this problem in terms of U, then you are left with this problem. The choice Z0 in BV amounts to choosing U0 in the space of random measures. And the fact that the solution becomes discontinuous with respect to x implies that Dirac masses will appear for positive time here, even if the initial data is continuous. So this is an interesting novel feature of this kind of problems, this dramatic loss of regularity. Even if you start from functions as initial data, then the solution can become random measure valued. So there is no hope to study this kind of problem taking initial values which are functions and keeps staying in a usual space of functions. So what you have to do is to study the natural space where to study this problem is the space of random measures because of this kind of phenomenon. This is what we did, in fact, in these papers. And since we are very interested in addressing the role of regularization, we considered that three different choices of psi, of the regularization, and those were chosen on purpose in the sense that the regularization becomes weaker when you go from this choice to this choice, which is a limiting case to this choice. Here, as a particular case, if you take theta equal to 1, you get the Sobolev regularization. So this does not degenerate at infinity, it grows at infinity, so the regularization is always very strong. This is a limiting case where you have a logarithmic growth, and this is still strong, but this is the case which corresponds to the argument, to the delay argument used by Barenblatt, and in this case you have a saturation of regularization at infinity. The problem is degenerate, so for large values of u, which of course are those which are most important for this kind of phenomena, since they describe aggregation, then you will not have regularization at all. And in this third case, because of the difficulty of the problem, we only were able to treat the one-dimensional case, as in the original paper, joint paper by Barenblatt and the others. Now, if you want to study, and of course, because of the previous remarks, we wanted to study this kind of problem where you have this regularization. We still call this quantity chemical potential. We want to study this problem in a space of random measures. Now, the first problem, the first question, a very naive question, of course, is the following one. Okay, you want to study a nonlinear problem in a space of measures, how to make sense of a nonlinearity of measures. This is ill-defined, of course. Okay, now what happens is that, in fact, the nonlinear part, the right-hand side, does not depend in our definition on the singular part of the measure. You see, formally, you have the nonlinearity is only in this right-hand side. And as for the right-hand side, we assume that it only depends on the regular part of u, so on some functions which is values at least in L1 of omega. So this is a function in the usual sense. This also is a function. And when psi is a power, we also require that the Laplacian of the chemical potential be a function L1. And so our definition of solution is this one, which is consistent with the discussion we had. And this is the duality for fixed time between these values, this trace and this trace with respect to omega for this choice of test functions. Now, the heuristic idea which is behind this definition is that because of the shape of the diffusivity, of the shape of phi, when u is very large, you do not have diffusivity at all. So this, when the measured valued character appears in the right-hand side, then it does not contribute at all to the diffusion. And this is an idea which goes back to the original paper by Barenblatt and the others. For logarithmic type, you have a similar situation, the same definition, but now the Laplacian of V is not a function, it is L infinity with respect to measures. And then for MC is bounded, the definition is similar, but much more complicated, since in this case, as we know from that example, singularities can appear as time increases. And there is a certain situation where we can describe the mechanism. Uniqueness results have been proven for power type or logarithmic psi. And apart from technicalities, what are the common features between these three choices? Okay, one feature is how we prove the existence. We use a family of approximating problems. We have a priori estimates uniform with respect to n. We pass to the limit properly, and so this is more or less standard. Another common feature which is interesting is the monotonicity of the singular part. We can prove anyway this inequality for any fixed test function. When time increases t1 less than t2, then the corresponding value of the singular part at t1 does not exceed the same quantity as t2. This means that when a singularity is present, either from the very beginning in the initial data or for positive time when it appears, then it never can disappear. It keeps being there. So there is a monotonicity of the singular part. This corresponds to the deregularizing properties of the problem. Now, what are the differences from the qualitative point of view? And this illustrates the different role of regularization. If psi is a power type, very strong regularization, then the singular part does not evolve in time. It is always constant. It is the same which was at the beginning. And this is clear from the very definition we used, since this singular part, this difference, is equal to this right-hand side, which is only a function L1. So it is at the same time absolutely continuous and singular with respect to Lebesgue measures. So it has to be 0, and so this is constant. And this happens since psi is very strongly regularizing the problem. But if psi is a logarithmic growth, then something begins to move. The singular part may increase, but it never appears spontaneously. Namely, the support of singularities, when in this case, are constant in time, but for every fixed support, along the support, there is a factor, which is a function time, and which increases, and in fact, it increases exponentially, depending on the values of the chemical potential. And then the third case, which is the physical case, the most interesting case, singularities can appear spontaneously. And just 1 minute to describe a possible mechanism for disappearance of singularities. Look at this set. This is a good set for fixed time. It is a set such that for every point there is a neighborhood where you do not have a singular part, and where, moreover, the regular part is bounded. So this is a very good set. You can prove two properties of this set. First of all, this set is steadily decreasing, and this is natural since singularities increase, so the good set decreases. There is a formal rigorous proof of this fact, but this is in agreement with the previous property of the singular part. And the second important fact is that on this set, the chemical potential is positive, and the chemical potential is 0 on the complementary set. So the chemical potential is always non-negative, but it is exactly positive here and 0 on the complementary set. Now, what happens? Suppose that for some time, since this set decreases, a new point, just a point for simplicity appears in this set. In this point, since it belongs to the boundary, you will have a V which is equal to 0, where V is positive somewhere else where it was already positive. And moreover, in this set, you have an elliptic equation. This can be rigorously proved. This equation is nothing but formally a rewriting of your evolution problem, since ut is equal to Vxx, and V is this chemical potential. Now, if you formally derive with respect to time this term and you plug this first equality, then you formally get this elliptic equation, which holds for every positive time. Now the conclusion is very simple. Suppose that a new point where V is equal to 0 appears, V has to be positive everywhere else, suppose, and then the Hopf lemma tells you that since at this point Vx is 0 but otherwise is positive, then Vx must have a jump, since V is 0 there, Vx has a jump discontinuity at this point. So you start from, say, from some interval where V is positive, Vx is negative, here V is 0, Vx is positive. At this point, you have a jump discontinuity of this value so that you have a Dirac mass for Vxs. So in this equation, you have a Dirac mass which keeps being there for subsequent times, and this is a possible mechanism, a very simple situation to describe how singularities appear. Of course, in general problem is how to address the formation of singularities, and I just give you the idea, why is this related to this kind of problem? Well, this problem here, by this formal transformation, if you make a formal time reversal, you get this relationship between the original equation and the new equation. And now, if you disregard the branch where phi is positive, you just regard this, then you will get exactly a problem like this. And what happens in the future for the original equation will appear in the past for this other. So the regularizing corresponds to regularizing properties. So to describe in generality the regularizing properties of our problem, you have to describe the regularizing properties of this. And now the problem is, suppose I have a solution of the problem with initial data, which is a measure, when will it be a function? And let me just mention that this dates to a very wide literature concerning measure-valued solutions, which goes back to these very old classical papers when T is a power type function. Thank you for your attention.
Я по-русски могу сказать, да? Два вопроса. Переведите?
Тогда я их переведу.
Ага. Так, масса Дирака появляется в одной точке или в нескольких точках? Масса Дирака.
Еще раз.
Масса Дирака появляется в одной точке или в нескольких точках?
Does the Dirac mass appear in one point or in several points?
The situation I was describing is a very simplified one. In principle, it could appear at several points. That depends on the initial data, of course.
Переводить надо?
Переведите.
Значит, изложен очень упрощенный случай, то есть в одной точке, но в принципе это может быть распространено и на случай нескольких точек.
Спасибо. Так, второй вопрос я задаю.
The second question.
Для каких значений параметров уравнения решение не аналогично кубической параболе.
Could you please tell us for which values of the parameters of the equation the solution is not similar to the cubic parabola?
Она не аналогична.
Not similar, not analogous to cubic parabola. For which values of the parameters of the equation?
It is not a matter of parameters, it is a matter of problem. In some problems, only a cubic light, to my knowledge, only a cubic light phi appears. The actual form of phi is not important, just the behavior at infinity and the number of zero. You can allow any finite number of zeros, but the behavior at infinity is what matters, and that's one situation. And then in other problems, you have a situation where phi does not go to infinity, but either it stabilizes or it goes to zero. The case where phi goes to zero, which is the actual case of Peruna-Malik case, is the worst one, since it is degenerate, and in that case, Dirac-Messi's random measure can appear in the solutions. In other case, you would get some better estimate of the solution, a priori estimate, so you do not have appearance of random measures, supposedly.
Я более кратко объясню. Значит, ситуация такая. Значит, дело в том, что кубическая парабола вообще приведена исключительно как пример. То есть,
пример,
да, то есть дело не в том. Дело в том, как ведет себя решение на бесконечности. Вот
понятно.
это более
Вот это
сложный
главный
случай,
смысл,
когда
да?
бывает. Да. И, значит,
понятно.
количество нулей.
Понял. Спасибо. Thank you.
Thank you.
Thank you.
If you have the applications in image processing, you would not like to get in dynamics of the process because it's time dependent also there. Appearance of data distribution because it would give spots. Therefore, probably all regulations of that who give data distributions would not be welcome for the image processing part. Have you studied the image processing too?
Not directly, but the case of phi in one space dimension is the case of image processing, that kind of phi.
But there one tries to avoid appearance of spots which comes from the equations, and so, because they, I can show you in other cases of where you really see it's not, it depends on the mathematics which one uses if the spots arise or not. And I have another question. One is, it would be also needed, especially also in filtration flow as well as in image processing for systems. Have you ever looked at that?
Systems?
Yes.
No.
Because
that's
this image processing is for gray value.
Mm-hmm.
But if you go to color, you have systems, and also we have it in filtration if you have multiphase. And we were looking at those type of problems. I would like to discuss that with you after that.
Certainly very interesting, but it's
it's needed. It's needed for equation.
I would suppose
image processing
it is
too.
very difficult.
Yeah.
Going back to your remark, I'm not saying that direct masses or measures will appear in any case. It will depend on the initial data in several situations. So perhaps the situation you have in mind, the right one would be.
But you have no result that you can say if this is fulfilled for the initial data, it will not appear. It will.
Yeah, we do.
You have?
Yeah, we
Okay.
do. Okay, we have a regularizing result for these related problems, which essentially depends on the behavior of psi at infinity, on the speed at which psi goes to zero at infinity.
Okay.
That looks reasonable.
Thank you.
Sure. I think other questions personally. 1 minute only.
My question is, my question is the following. do you know something about the, say, capacitary or Hausdorff measure size of the singular set of US?
No. No, but that's a very good question in the sense that we only dealt with a one-dimensional case, and my discussion there relies on the strong maximum principle. And now generalizing a strong maximum principle in higher space dimension would be certainly related to the capacity of the singular set.
Okay.
So I think.
Okay, thanks.
Okay. Thanks again. Our next speaker, Professor Taymanov, the title of his talk, Mutter transformations for two-dimensional differential operator.
Это слайд назад, это самая указочка. Все, уже включено. Если хотите, можете.
Okay, first I would like to thank organizers for inviting me to the conference, for giving the possibility to give this talk. In a sense, it will be extension of my talk which I gave 6 years ago, because at this time we did have some joint results with Tsarev about Mutter transformation of Schrödinger operators, and recently I did something about Mutter transformations of Dirac operators, and the announcement of this result and some preliminary article were posted to arXiv exactly this week, so I never spoke about that, and I will start with the same page which I used already 6 years ago on the same conference. So just to remind, what is the Darboux transformation? The Darboux transformation is the trick when you can construct one integrable Schrödinger operators from another ones. It was rediscovered many times. It's known as factorization method, but by Infeld-Hall in elasticity theory. It was used by Schrödinger. It was used by Dirac when he computed the spectrum of the harmonic oscillator in his principles on quantum mechanics. In spectral theory of differential operators, it's called the Cram transformation due to the seminal article by Cram for middle 50s. And it is as follows. As soon as we have a solution omega, or the equation h omega equals 0, the h is just the Schrödinger operator of one dimension, then every such a solution defines a factorization of h into the product of two operators of the first order. A top and A, where is A top is just formal transposition of the operator A. So this is the first order operator with potential V. V is the logarithmic derivative of omega. The Darboux transformation consists just in swap of AT and A. So let's just swap them. We obtain another Schrödinger operator with another potential U tilde. And the transformation, extended transformation of eigenfunctions, formal eigenfunctions, formal solutions of this equation. So if we have a psi which satisfies h psi equal e psi, so in this case we can take any formal eigenvalue e, then the psi tilde, which is just the result of the action of A on the psi, would satisfy with the same equation for the new potential. So in the principles of quantum mechanics of Dirac, it was called birth and annihilation operators. So it's birth, there was going to give birth to another particle. And this Darboux transformation was introduced originally by Darboux in different terms, not in terms of factorization operator, as the result of one-dimensional reduction of the Mutter transformation. Actually, Darboux wrote a very short article on 3 pages in Contrendu in 1882, saying that some transformation by Mutter, another French mathematician, differential geometry actually, who used his transformation in differential geometry, and introduced his transformation in 1876, then it has a very nice one-dimensional reduction. That's exactly what Darboux did. So I follow to the Mutter transformation. Mutter transformation did work with two-dimensional operator, and the solution of this on the level also 0. H omega here would be minus Laplace plus u. This would be H operator. Actually, Mutter did work with hyperbolic operator, not Laplace, but dx dy. But since it's a formal analytic procedure, so we can assume that x is z and y is z bar, and reduced his transformation to the elliptic case. So if we have the two-dimensional Laplace operator, then the Mutard transformation is defined as follows: h tilde equal minus Laplace u in minus 2 Laplace of logarithm omega. It gives you a new operation. And if psi satisfies this equation is psi equals 0, then the function theta, which is defined through this system, it's defined modular the summons kind of 1 over omega, so it's not unique. Then it satisfies new equation. So if we have its some operator for which we know all the solution to this equation h omega equals 0. For instance, if potential u is vanishing, then it's just harmonic functions. Then they take, for instance, can take any harmonic function, can use this transformation and obtain another operator with non-trivial potential, for which we can compute all zero energy level, all solution of this equation h tilde equals 0. So this was procedure by Mutard, kind of very nice integrable procedure, which is now kind of attributed to integrable systems, but not very widely used. The Mutard transformation describes the formation only of eigenfunctions with zero eigenvalues, because in Darboux transformation you can subtract from U the eigenvalue E and work with an extended for all eigenvalues. The action of the Mutard transformation eigenfunction is multivalued. It's defined modular multiples of 1 over omega, actually modular summons of multiples of 1 over omega. And the third remark is just the article of Darboux. If we just write down the Mutard transformation, assume that U depends only on one potential x, and omega will be fx exponent kappa y. There is kappa squared is the eigenvalue of one-dimensional Dirac operator. Then they have the Mutard, then they have the Darboux transformation. It was interesting to use the Mutard transformation for finding some interesting examples of operators, and we tried to do with that with Sergei Tsarev, and I reported about that 6 years ago. But here I would like to remind briefly some results, because they would be extended to other cases later. So I already mentioned that if we have the harmonic functions as the zero energy level of the operator with a trivial potential, when we can construct new potential. But since it would be logarithmic, Laplace of a logarithm of a harmonic function, either it would be, it wouldn't be fast decaying, either it would have singularities. It appears that we can do the double iteration procedure. If they do it in some convenient, smart way, we can get the potential with no singularities with good spectral properties, such that for this two-dimensional Schrödinger operator, everything is well defined. There is spectral. There is S matrix, there is a kind of, spectral expansion of this operator, so everything is good. So in this case, we're using this double iteration. So we're starting with two solutions, omega 1 and omega 2. To every way you do correspond the Mutard transformation. Every solution is mapped to another one, theta 1, theta 2 by this transformation, and then they apply iteration corresponding to this solution. This diagram would be commutative if the theta 1 would be chosen properly. This commutative diagram is known to differential geometers from 19th century. It's called Bianchi permuttability theorem, because Bianchi, famous differential geometer, did discover these permuttability properties for many other transposition, Backlund transformation, and other transformations, so it's quite well-known fact. Its permuttability is widely used in the so-called discrete differential geometry developed mainly by a group in Berlin, by Babenko and Souris. So because this discrete integration is in many respects it's based on this transformation of operators. And moreover, as soon as they're doing this procedure, we immediately obtain two solutions, psi1 and psi2, of the equation which lies on the zero energy level. H psi1 equals 0 and H psi2 equals 0. So it lies in the kernel. Our idea is to get such a potential, was to get such a potential U, which is for which the spectral theory, everything is well defined, or this scattering theory actually well defined, scattering procedure, and for which, so they have to decay rather fast, and for which these functions would lie in LL2. So in this case, we will get the discrete spectrum at the 0 level. So it's impossible in one-dimensional case, and it appears that's possible in this case, and that was shown by explicit procedure. But before going to it, before to expose our results with Tsarev, I would say that the original Mutar transformation was defined for this equation, and it has the following meaning. Let Rxy will be surface enough free with asymptotic coordinates xy. Then this procedure was using for constructor, then it appears that this function psi satisfies this Mutar transformation. In differential geometry, it was called Mutar equation, 19th century. And then they apply the Mutar transformation to these two solutions of this equation. We obtain another solution of these equations. One can notice that the asymptotic coordinates are defined on negatively curved surfaces, and the main idea of many geometers, then they're trying to develop all these procedures, was to construct the immersion of Lobachevsky or hyperbolic plane into R3. So many people were not satisfied that the Lobachevsky geometry is realized on the two-dimensional surface, which is not yet immersed into R3, and they tried to construct explicit immersions. That was a long series of events, but the first was probably Beltrami, pseudosphere, but it has a singularity. It appears that many other examples, many other procedures do lead the negatively curved immersed surfaces with singularities, and then it appears that it's impossible by Hilbert theorem at the beginning of 20th century. So that's the negatively curved surface with constant negative curvature cannot be immersed into R3. So that's the main interest in these procedures by differential geometers was lost. But now some of them were discovered or they're used in the framework of integrable systems theory. So this is our two-dimensional rational solitons. We're starting with zero potential, and by iteration we construct two-dimensional rational solitons which are fast decaying. They decay actually for good scattering theory. It's necessary to have such a decay of potential in two-dimensional case. But in our case, they even decays as 1 over R6. All potentials, all these functions are rational. And we have two explicit eigenfunctions with lies in the kernel, which is the first and probably known example of two-dimensional operators with fast decaying potential and non-trivial L2 kernel. And then they came to the second part of the story, the construction of blown-up solutions to the Novikov-Veselov equation. The Novikov-Veselov equation has this form, and it is the one-dimensional, it's two-dimensional generalization of the Korteweg-de Vries equation. So it reduced to E to assume that the potential depends on X and the additional potential V coincides with U. So then they have the two-dimensional, then we have the Korteweg-de Vries equation, and the Novikov-Veselov equation, just the two-dimensional version of this KdV equation, which is different from KP, because in KP equation, the two special variables, they do not have the same sense. It's obtained, it's kind of some expansion, small perturbation in the direction Y. So, but here they're kind of all the special variables x and y kind of do have the same meaning, and this is a very nice equation, which appears to have some relations to algebraic geometry of Riemann surfaces. We have very nice properties, and it has it is a compatibility condition of this system. H psi equals 0, whereas H is a Laplace operator, and it's represented by Manakov triple. What is the meaning of Manakov triple? If it's HT equal commutator of H and A, two differential operators plus BH. In this case, the BH is the summand which differs it from the Lux pair, Lux representation. It appears that if we would like to construct Lax pairs for two-dimensional operators, it's kind of not a theorem by Manakov, but some of his results. If we'd like to obtain non-trivial examples, then the potential has to split into the sum of one-dimensional potentials in special variables. So if we'd like to get something non-trivial and to obtain the Lax pair, then with a which leads to non-trivial soliton equation, you have to add this BH summand, and in this case it's this transformation, this evolution preserves not the whole spectrum of the H, but just only its zero level. So the solution of the equation H psi equals 0, they're transformed by this system. And other points of the spectrum can deform. So this is, and this system is invariant under the invariant Mutard transformation, so extended Mutard. So Mutard transformation can be extended to transformation of solutions of the Novikov-Veselov equation, because you see there is this compatibility condition of H omega equals 0, so assume that the H omega equals 0, we have some psi, which evolves by this equation, and every point, at every moment of time, we're doing the Mutard transformation of this operator, and we get new potential, new transformation, which again would satisfy the Novikov-Veselov equation. This is the term which depends on T is quite large. Every there has some additional correction terms. So even in the case if U is constant, due to some non-trivial term, is stationary due to some non-trivial terms coming from psi, we can get non-trivial evolution at the end. And so if there are two homomorphic Z functions, P1 and P2, which satisfy this equation, then the double iteration of the extended Mutard transformation gives a solution. That P1 and P2 is just harmonic functions, so such that omega 1 is just real part of P1 and omega 2 is real part of P2. So this is a very nice procedure for constructing solutions. And after applying to this construction to this pair of polynomials, we obtain a rational solution which decays in R minus 3 in non-singular up to the critical time, and then it becomes singular. So there is a blow-up procedure which is very integrable, very natural. And I would like to notice that the Cauchy problem for KdV is well-defined for good initial potentials. So there is Mennikov theorem which says that even the first potential, if the potential has at least 6 derivatives, then there is a regularity theorem for solutions of KdV. We even don't have in this case to assume that U is fast decaying. We only have to assume that it's regular. But here we have this real analytical potential, initial time, the Cauchy problem, that goes and then it blows up. So the situation of this blow up, this scenario is very simple because it's given by rational functions. And we have to pay attention that there is the first integral, the trivial conservation law, just integral of potential U, all the two-dimensional space. So this, the integral has to be preserved. So this oscillation starts at 2 points when we're coming to this critical time. And then at this critical time, the potential is not defined at this point. It equals 0 along these curves. It's, if we're going inside to these sectors, to this critical point, then it has different limits. It alternates plus or minus infinity. And, but the mean value of this integral is preserved. So, but it stays, singular for other times above this critical time, 29/12. So this is the blow up of two-dimensional generalization of Korteweg-de Vries equation. And now the idea was to look the same for the modified Novikov-Korteweg-de Vries equation, for which the first integral is different. It is integral of U squared. So it's very special. First integral, it's a squared integral norm. And this equation is also represented by means of the Markov triple, but in this case we have to replace Schrödinger operator by two-dimensional Dirac operator D with potentials. Here D and D bar are derivative with respect to the complex parameter on the plane, Z and Z bar. So it appears that in 2001, along Yu, Liu, and Shikun Wang introduced the Mutar transformation, which generalizes Mutar transformation for Novikov-Veselov. But this procedure, these formulas are quite bulky. Even in the short notice in some physical journal, it said that the transformation they cannot write down the explicit proof or that the transformation gives you the transformation of solution of a modified Novikov-Veselov equation, and they only checked it by Maple program, which was also quite hard. And so I do not give the explicit formulas for this transformation here. They're quite bulky. But the idea is the following. It's the same, basically. To any solution psi, the equation, or to this equation, and three real constants, which are coming to the procedure. One can correspond to the Mutar transformation of the Dirac operator and recompute all solutions of the equation H psi equals 0. So we have to split now the transformation of the Dirac operator over potential transformation of solutions, because even in the previous case, this formula for transformation of the Schrödinger operator was quite simple, and the transformation of solutions was much more complicated. So the modified Novikov-Veselov has this form, also Markov triple, and if they assume if U depends on X and resolve this constraint by simply assuming the D equal U squared, then this equation reduces to modified Korteweg de Vries equation. So that's why it's called the modified Novikov-Veselov equation, because actually it generalizes MKdV in the same sense that Novikov-Veselov generalizes KdV. And this equation was introduced by Leonid Bogdanov, at this time graduate student in Landau Institute, and Chernogolovka at the beginning, in the middle of 80s. So first we would like to explain what is the meaning of this transformation of the potential of Dirac operator. It appears that it's very geometrical. So there is some formulas by Konopelchenko, Eisenhardt, which I shall use here. They say that to every solution psi of the equation d psi equals 0 with U real valued, we can reconstruct such a surface. So there is a surface, so this is psi 2 bar. We can install it into these integrants. We get a three surface immersed into a free. The induced matrix is locally Euclidean. The conformal factor is computed from the psi, and the potential is the square root of the conformal factor times the mean coefficient over 2. So these formulas were known, widely known for U vanishing. In this case, this Weierstrass representation of minimal surfaces. And then I showed that actually every surface, even closed, compact surface, can be reconstructed by these formulas, but in this case, psi has to be defined as a section of the spinor bundle, or the some model surface. So that's quite a general presentation of these solutions. But here we have the potential of the surface. Potential is attributed to the surface with a fixed conformal parameter on it. And what gives this Dirac transformation? So you see again that Dirac operator comes into this picture. So, and I would remind that's the geometry of the Mutar transformation. So to every solution psi and three constants, actually it's exactly these three constants which are coming to this procedure written by this Chinese physicist, we can correspond the surface immersed into R3. Actually, psi 1, psi 2 defines the Gauss map on this surface, or it's kind of reconstruction for the Gauss map. And this is a procedure so the surface defined up to translation. So if we translate the surface in R3, then the Gauss map would be the same. This is the meaning of these three constants. So and there is the Möbius inversion. I put here minus just to make it orientation preserving. So it's inversion of the free space, which maps R3 with completed by infinity point, in this case into S3, it maps into S3. So the origin is mapped to infinity, so it would be conformal transformation of a three-dimensional sphere. So let's take our surface U, our surface S with potential U and conformal parameter Z on that, and let's take its inversion. So we get another surface, sigma. Z again would be a conformal parameter on this surface, and U tilde would be the potential, or this conformal the potential of this surface. Then one can check, then one compute U tilde, and then compute this transformation of the Dirac operator by this physicist, and show by direct computations, quite, not very short, that it's the same. So actually, this is a Muttard transformation for Dirac operator has a very simple geometric meaning. It's just the potential of inverted surface, nothing else.
Sorry, but is it some very special Muttard transformation, I think?
Yes, very special, just one for this Dirac operator, yes. But it's only one known for it, explicitly computed. So that's okay. We can do that's also this transformation again in the same in this geometric terms. But it appears that then we compute in terms of psi1, psi2, we would get exactly this Muttard transformation by these Chinese mathematicians, physicists. And now I would like to construct a blown-up solution for modified Novikov-Veselov equation. It appears on arXiv this Thursday, so that's 3 days ago. Short announcement, and it's very simple. Now. I'm starting using this effect which we noticed with Tsarev, that even the stationary potential can give non-trivial solution. So attacking the stationary potential U equals 0, it corresponds to minimal surfaces. So we have a lot of minimal surfaces. And then I took the minimal surface, which is defined by a very simple spino, Z1. So this minimal surface is well known. It's a Nepper in a minimal surface. It's immersed. It's not embedded. And there is analog, which I would write down because it wouldn't enough, probably 2 pages, probably 2.5 would be to show the how this term is generalized for Dirac case. So it's quite large formulas. But exactly for minimal surfaces, it's shortened rather briefly, but for Nepper surfaces, it shortens even more. And we have very simple geometry behind that. So what we shall do, we shall take the Nepper surface, defined up to translation, take one of its position, and do the following. So the Muttard transformation or the solution, or the stationary solution would be as follows. They take the Nepper surface, which didn't pass through the origin of the map. So this Nepper surface is minimal, U equals 0. So we take inversion of it. Inversion would be a sphere in S3, in R3, which is branched at one point, with one branch point at which induced metric vanishes. You don't have a question yet? So now this Muttard transformation looks the following. We start the rigid translation with a constant speed of this Nepper surface. At one point, it hits the origin. So in this case, the origin is by inversion is mapped to infinity, and we have the singularity point of the deformed potential. Then it passes through the origin, going further. There are no singularities. So how looks like this is actually, this C is specially chosen. This is actually the time when the point would hit the origin. Then the Nepper surface would hit the origin, and they have the following. The functions U and V, solutions of this modified Novikov-Veselov equation, are really analytical elsewhere outside the single point, y equals 0 and t equals c, constant, at which they are not defined, and this function U has different finite limit values along different rays. Actually, it's just the asymptotics of this quantity E square root of conformal factor times mean curvature of this inverted Nepper surface. Then some point of it goes to infinity, so they have points at infinity, we have different asymptotics of this surface. So this is the median. And the function's decay is SR minus 2. We cannot improve that, but it's still ln2 for all fixed times. And there is the first integral, u squared. What is the first? The median of the first integral is my observation. This is just the Willmore functional of the surface. It's known for in biophysics as Helfrich functional, but actually Helfrich functional, they do have some additional constants. So but Helfrich functional was introduced due to the Willmore. So in the original article by Helfrich in '73, he says that he using this geometric functional for trying to extend it to some meaningful functional which describes the behavior of the boundaries of cells. So, and this is the first integral. So it is the conservation law at the periods of time where it is defined. So we have one period of time where it's not defined. So first, what is it for these times when t doesn't equal to c? Then it is the Willmore functional of this branch sphere, or this sphere with one branch points. And it would be 3 pi. It could be easily computed. Actually, it's 1/4 of the Willmore function. It would be 3 pi. It could be easily computed by the Gauss-Bonnet theorem. And then it stays the same outside it. So that's, but at this one point, when t equal to c, an epi surface hits the origin, and by inversion, this point is mapped to infinity. So we have point at infinity, it's no more compact, and exactly at this moment of time, this first integral jumps to 2 pi. Then it goes through the origin, it jumps back to 3 pi and stays 3 pi forever. So it's very simple rational solution of this complicated soliton equation with such nice property and such simple and scenario of blow up, which has very simple geometrical meaning. And this is just an upper surface. It's defined by these formulas, these explicit formulas. So let us consider the family of this transferred. So U10 would be 0, U30 would be 0, and he assumed that the original point is C. So C could be 0. So, and then we have just the translation. So the U0 would be C minus T. That would be T translation, the rigid translation along the y-axis. So then it hits, the inversion maps into the non-compact surface. It will have different asymptotics of the potential, and we'll have the blow up of the solution of the modified Novikov-Vasilov equation. So that's so it appears that the hint that such a solution has to exist was correct, but the only abstraction which did appear at this time was the behavior of conservation law, U squared, but it appears we can avoid it, so it's just the conservation law jumped exactly at this point because it is a singular point which is supported just at one moment of time. That's actually the result which I wanted to expose on my talk, and I would like to thank you for your attention.
Переведите, ладно? Так, хорошо. В проблеме Шрёдингера вы выполнили переход от потенциала U нулевое к U. Дальше говорю. А теперь вот вопрос.
In the Schrödinger equation, you passed from
как выглядит ансац для U? Вы его не указали, этот ансац.
Please show the ansatz for U.
Ну, формула, короче говоря, для U. У вас только картинки.
Вот, ну, когда мы...
А сама формула какая? По какой формуле вы эти расчеты делали?
Вот по этой. Вот подставьте это сюда, поменяйте их местами, получите новый потенциал.
The ansatz is
Но
shown.
самой-то формулы нет у вас для потенциала.
Но это будет сейчас, это v квадрат, если вот это будет v квадрат минус vx, то это будет v квадрат плюс vx.
Вы это использовали в расчетах, да?
Да, да.
Спасибо.
Ну, я думаю, действительно, чтобы сократить все формулы, потому что формул было бы много, а я не хочу, чтобы они забивали голову.
Other questions? No? Let's say again.
Thank you.
Great.
Михаил Борисович, вы хотели потренироваться? Где он?
40 minutes.
Михаил Борисович, я вас не вижу. Ну нет, так нет. Ага.
Session of this morning with the pleasure of introducing Professor Sevriuk, and we'll heard about CAM theory, which is an important subject here. Vyot.
Okay, first of all, I would like to thank the organizers of this conference for their kind invitation to present a talk here. So the title of my talk is so there is no pointer, I don't know why. Okay, thank you. Okay, so the title of my talk is The Classical Game Theory in the Last Decade, a Slow Progress. Here I tried to draw a family of invariant tori, the key object in the game theory. And first of all, I would like to say some words what game theory is about. So game theory, named after its founders Kolmogorov, Arnold, and Moser, is the theory of quasi-periodic motions in non-integrable dynamical systems. It started in 1954 with this famous note by Kolmogorov, and so this year is exactly the 60th anniversary in the history of game theory. This year is the 60th anniversary of the founding of game theory, and the last decade, from the middle 2004 to the present moment, is precisely the 6th decade in the history of game theory. We will consider only the finite dimensional game theory, that is, game theory for dynamical systems with finite dimensional phase space. I would like only to say that the infinite dimensional game theory for partial differential equations, founded around 1985, is another world, actually. And there, the dimension of invariant tori, the number of frequencies of a given motion, can be either finite or infinite. So the key object in this theory is an invariant n torus carrying quasi-periodic motions with some frequency vector, a so-called quasi-periodic invariant torus. N can be any non-negative integer. For n equal to 0, we obtain equilibrium. For n equal to 1, we obtain closed trajectories. And for n greater than 1, okay, we obtain the main object of this theory, an invariant torus of dimension 2 or higher. So let X be the vector field in question on the phase space M. Below always X will be the vector field in question. Let K be some embedding from the standard n-dimensional torus to the phase space that satisfies this invariance equation. And this invariance equation, this functional equation, expresses simultaneously two things. First, the image of this embedding is an invariant n torus of the flow of our vector field, and this torus carries conditionally periodic motions with frequency vector omega. And second, what is very important, K parameterizes our torus in a very good way. That is, in the natural coordinates taken from the standard torus, the equations of motion take this form. Phi dot is equal to omega. One can also consider the variational equation along this torus on the tangent bundle of the torus. This variational equation has this form and it also plays a fundamental role in the KM theory. The frequencies, omega 1, omega n, actually they can be any real numbers if they are incommensurable if they are independent over rationals, then one speaks of quasi-periodic motions. One usually considers not just incommensurability, but strong incommensurability. For example, Diophantine motions, which satisfy this infinite system of inequalities. For n greater than 1, small divisors appear, that is, small linear combinations for large integer vectors k. And now we can say what KM theory explores. So KM theory studies generic occurrence of witness-smooth, counter-like, m-parameter families of invariant entori carrying quasi-periodic motions with strongly incommensurable frequencies, for example, with Diophantine frequencies, in vector fields with given conservation laws and symmetry properties. For example, in Hamiltonian vector fields, in reversible systems, and so on so. Now I have to explain what these words, witness-smooth, counter-like, mean. Okay, so let us consider the set of Diophantine frequency vectors omega with fixed gamma and tau. Then this set is nowhere dense, but it has positive Lebesgue measure if gamma is sufficiently small. And this property of being nowhere dense and having positive Lebesgue measure is the Cantorian property. And so the parameters that label our tori range not in some open set of the Euclidean space. They range over some nowhere dense set of positive Lebesgue measure. And this is the property of being counter-like. But it turns out that all the functions that determine our tori, the embeddings, frequencies, maybe some invariant sub-bundles of the variational equation, so and so, all these functions that are defined in this Cantorian set can be extended to smooth functions defined in some open set containing this Cantorian subset. And this is the property of being witness-smooth. The families of tori are often organized into complicated hierarchical structures. For n equal to 0 and 1, the families are smooth rather than witness-smooth counter-like because there are no small divisors. Also, the tori can be either reducible or non-reducible. That is, the variational equation can be reduced to constant coefficients, and it is possible that it cannot be reduced. Here I wrote the meta-reason, some philosophical reason, so to speak, for the ubiquity of invariant tori carrying conditionally periodic motions. Any finite-dimensional connected compact abelian Lie group is a torus. All of this pertains to KM theory for invariant tori of flows. There is also KM theory for invariant tori of diffeomorphisms. Here, the only special dimension is n equal to 0, where there are no small divisors, but I will not speak about KM theory for mappings in this talk. All the theory can be run for various smoothness classes, that is, for analytic systems, for infinitely differentiable systems, for finitely differentiable systems, and for various structures, the so-called contexts. So you can see context here. I will explain below what the words conformally Hamiltonian and pre-Hamiltonian mean. But of course, the most important context, the prototype context, is the realm of Hamiltonian vector fields. Here, just to recall, I written the definition of Hamiltonian differential equations, so one should consider the convolution of the symplectic form with our vector field. If this form is closed, then one obtains locally Hamiltonian flows. If this form is exact, then one speaks of Hamiltonian flows, and the primitive function is just the Hamilton function. one can always introduce, at least locally, Darboux coordinates in which the symplectic form takes this form and the equations of motion take this form. Of course, all these things are very well known. But this crucial fact of fundamental importance of the Hamiltonian K-M theory is not so well known. The Hermann lemma, which actually goes back to Moser's paper of 1966. So if we have an invariant torus of a Hamiltonian vector field, if this torus is quasi-periodic, if it carries conditionally periodic motions with incommensurable frequencies, and if the symplectic form is exact, then this invariant torus of a Hamiltonian flow, or even of a locally Hamiltonian flow, is automatically isotropic. That is, the restriction of the symplectic form to this torus vanishes. And in particular, of course, the dimension of this torus cannot exceed the number of degrees of freedom. And the proof is very simple. So one should consider the flow on this torus in the normalized coordinates. This flow preserves the restriction of the symplectic form. Since each trajectory of this flow is everywhere dense in the torus because of quasi-periodicity, this form has constant coefficients, but this form is exact, and consequently, it vanishes. And now one arrives at the main principle of the K-M theory for Hamiltonian systems. So in generic Hamiltonian systems with n capital degrees of freedom and with an exact symplectic form, one encounters generically n parameter families of isotropic invariant n tori for each n from 0 to the number of degrees of freedom. These families are, of course, Cantor-like and Whitney-smooth. And now I have written an infinitesimal heuristic argument why isotropic invariant n tori in generic Hamiltonian systems are not isolated, for example, but they are organized into n parameter families. These tori are said to be Lagrangian or maximal if their dimension is equal to the number of degrees of freedom, and they are said to be lower dimensional if their dimension is less than the number of degrees of freedom. For non-exact symplectic forms, exotic families are added of co-isotropic invariant tori and atropic invariant tori. That is, the invariant tori that are neither isotropic nor coisotropic. And these are discoveries not rather recent. And now I proceed to the progress in K-M theory in the last decade. Of course, this progress is slow compared with the heroic period of the 60s, but definitely not compared with the preceding decade, with this decade. The main achievement of the decade before last, of this decade, is Gevrey regularity of Whitney-smooth families of invariant tori in Gevrey or analytic systems. Here I wrote the definition of Gevrey functions. They are just infinitely differentiable functions with whose derivatives grow not so fast. So if kappa is equal to 0, one obtains just analytic functions, and for positive kappa, one obtains Gevrey functions. So before the fundamental discoveries by Popov, people thought as follows. For example, if we have analytic systems, that the tori themselves are analytic, and the families of these tori are infinitely differentiable, and nothing can be said more. But now we know that these families are not only infinitely differentiable, they are also Gevrey regular. But the main achievement of K-M theory in the last decade, in the sixth decade of the history of K-M theory, is the so-called a posteriori format for constructing invariant tori. This is a special collection of methods and approaches for finding, for constructing invariant tori in Hamiltonian systems, and not only Hamiltonian. Also, this collection of methods is called game theory without action angle variables or parameterization methods in game theory. Here you can see the main contributors to the a posteriori format. These contributors are listed here in a more or less chronological order. Actually, these ideas go back to this paper by Giorbo, Delayabi, and Zhou of 1999. And also, I would like to say that soon a lengthy, detailed survey of these methods will appear, this survey. And now I would like to explain what this means and to compare the conventional perturbative setting for finding Whitney-smooth counter-like families of quasi-periodic invariant tori, the setting that actually goes back to Kolmogorov, and the new a posteriori approach, point by point. Actually, there are many methods of proof in game theory. There are the so-called direct methods. There are methods based on infinite-dimensional implicit function theorem, but I will compare just the most widespread method, perturbative method, that goes back to Kolmogorov, and the new a posteriori format. So first, an ideal object. In the perturbative approach, the ideal object is a partially integrable system which admits a smooth family of invariant tori carrying conditionally periodic motions. So generically, one has Whitney-smooth counter-like family of invariant tori, but some exceptional systems admit smooth families of invariant tori. These systems are called partially integrable, and this is the ideal object, so to speak, within the traditional approach. In the new approach, in the a posteriori format, the ideal object is completely different. This is a collection of a Diophantine vector. This functional equation of an embedding of the standard torus to the phase space, which expresses that the image of this embedding is a quasi-periodic invariant on torus with this frequency vector omega, and this K parameterizes this torus in a good way, and probably some additional functional equations for parameterizations of invariant subbundles of the variational equation along our torus. Then the coordinates. In the perturbative approach, one works in a special coordinate frame adapted to the partially integrable system equation. For example, if one has Liouville integrable system, completely integrable Hamiltonian systems, then one works in action angle variables. In the a posteriori method, one works in any coordinate frame will fit for the phase space structures. For example, in any Darboux coordinates in the Hamiltonian context. And no connection with our vector field is assumed. One does not work in action angle variables within the a posteriori approach. One works in the initial variables, and this is very suitable. Then, third, a starting object. In the perturbative approach, a starting object is a small perturbation of a partially integrable system. In the a posteriori approach, the starting object is an embedding K of the standard torus to the phase space that satisfies the invariance equation approximately. So, a starting object in the a posteriori approach is an approximately invariant torus, and similarly for parameterizations of invariant subbundles of the variational equation. And the system is not assumed to be nearly integrable at all. So we have a Hamiltonian system. In this system, we have an approximately invariant torus, and we work with this torus, and nothing more. No action angle variables, no near integrability, nothing like that. The fourth point, the infinite iterative Newton-like procedure. So in both the approaches, the theorems are proven by constructing some infinite iterative procedure with accelerated convergence. The current term is more or less the square of the preceding term, at least if one does not take small divisors into account. But these procedures are very different. In the perturbative approach, one constructs a sequence of nearly identical coordinate transformations whose definition domains shrink down to the desired torus, like this. And the perturbation terms reduce quadratically during this procedure. In the a posteriori approach, one constructs a sequence of small corrections to be added to the embeddings in such a way, and the errors reduce quadratically. Then, the basic principle. In the perturbative approach, the basic principle is as follows. A majority of the unperturbed invariant tori of a non-degenerate, in a certain sense, partial integrable system persist under small perturbations. And this is the way how one obtains invariant tori in generic systems, because we have a very special system, an integrable system, but its perturbation is already generic. In the a posteriori approach, the main principle is as follows. Near a non-degenerate, approximately invariant torus, there is a truly invariant one. And the sixth point is suitability for computer implementation. The perturbative approach is quite hard to implement because coordinate transformations are difficult to be performed numerically. But the a posteriori approach is very easy to implement. And here you see some numerical characteristics of such implementations. And in fact, effective algorithms have been already developed and described in many situations. Actually, all this approach is very oriented to applications, to computer applications. Approximately invariant tori within the a posteriori approach could be unperturbed invariant tori for nearly integrable systems. And that is why a posteriori KM theorems imply the perturbative theorems. But actually, such approximately invariant tori could come from numerical calculations, from formal expansions, and so on and so. Now, some important examples. This is the first detailed paper where KM theory is developed within the a posteriori approach. Here, one considered Lagrangian tori of Hamiltonian flows and exact symplectomorphisms. So one has phase space of dimension 2n, the symplectic form written in Darboux coordinates, and an invariance equation which is satisfied by an embedding k approximately with some small error e, small in a certain norm. Okay, so one can consider different norms in all the science, different smoothness classes, and so on and so. And here I've written some formulas just to show you how the non-degeneracy condition looks in this case, where there are no action angle variables, there are no near integrability. So one should develop this matrix valued function S, and the average of this function over the torus should be invertible. This is just a matrix. Its determinant should be other than 0. This is the non-degeneracy condition in this setup. And if this condition is satisfied, and if the error is sufficiently small, then near the initial embedding, there is an embedding which satisfies the invariance equation precisely. Near an approximately invariant torus, there is a truly invariant torus, according to the basic principle. An example, if one considers nearly integrable systems, and if one tries to write this non-degeneracy condition for nearly integrable systems, then this matrix S will be constant, and it will coincide with the Hesse matrix the matrix of the second derivatives of the unperturbed Hamilton function, so the non-degeneracy condition would be that this Hessian matrix is invertible, that is the Hessian of the unperturbed Hamilton function H, which depends only on actions. The Hessian of this function does not vanish. So we have the conventional twist condition, that is the Kolmogorov non-degeneracy condition. For this particular case, the non-degeneracy conditions from the a posteriori approach and from the conventional theory coincide. Also, within the a posteriori approach, there is such a great thing as the local uniqueness. So if we have two embeddings that determine two invariant tori, two truly invariant tori with the same frequency vector omega, and if these embeddings are sufficiently close to each other, then they coincide up to a small shift. And this great theorem has the following two corollaries. First of all, the so-called bootstrap of regularity of invariant tori. So, if our system is analytic, and one has in this system an invariant torus, and this torus is sufficiently smooth, the word sufficiently should be understood depending on the Diophantine exponent of the frequency vector, then this torus is automatically analytic. And the idea of the proof is very simple. One should approximate our embedding by an analytic embedding, which satisfies the invariance equation approximately, of course. But according to the analytic a posteriori KM theorem, there is an exact analytic solution of the invariance equation. It will be analytically close to K hat and smoothly close to the initial embedding. Then this embedding and this embedding will coincide, and since this embedding is analytic, the initial embedding is also analytic. Of course, the same bootstrap of regularity exists just for systems of high smoothness. If you have a system of high smoothness and a torus of low smoothness, then this torus is of high smoothness automatically. And second, the second corollary is that KM for diffeomorphisms for mappings implies KM theorems for flows. But I would not like to dwell upon this. Now, in this paper, one considered hyperbolic lower dimensional tori of Hamiltonian flows and exact symplectomorphisms. So, one has a phase space, and in this phase space, one has an invariant on torus with some Diophantine frequency vector and with stable and unstable invariant sub-bundles of the suitable rank of the variational equation along the torus. And also some non-degeneracy condition holds, but all this is approximate, not true. Our torus is invariant only approximately. These sub-bundles are invariant only approximately, and so on so. Then, nearby, all this structure exists genuinely. There is a truly invariant torus with truly stable and unstable invariant sub-bundles, and so on so. What is also important here, that the stable and unstable invariant sub-bundles of the variational equation are not assumed to be topologically trivial, and a fortiori, the hyperbolic part of the variational equation is not assumed to be reducible to constant coefficients. Then, in this paper, one considered elliptic lower dimensional tori of Hamiltonian flows. Here, one considered not an individual Hamiltonian system, but a one-parameter family of Hamiltonian systems parameterized over some interval of the real line, and approximately for each value of this external parameter mu, one has an invariant n torus with some frequency, with some Diophantine frequency vector, one and the same for all values of this external parameter, and with reducible elliptic invariant subbundle of appropriate rank of the variational equation along the torus, with some Floquet exponents. That is the eigenvalues of the constant matrix of the variational equation. And some non-degeneracy conditions hold. Then, for values of this external parameter, in a Cantorian subset of our interval with nearly full Lebesgue measure, near this structure, one has a genuine structure. So one has truly invariant torus with frequency vector omega, a truly reducible elliptic invariant subbundle of the variational equation with some Floquet exponents close to the original Floquet exponents. A one-parameter family of systems is needed to overcome the normal internal resonances between the internal frequencies and normal frequencies. Now, we leave the realm of Hamiltonian systems, and in this paper, one develops KM theory for conformally symplectic systems within the a posteriori approach, of course, for Lagrangian tori of conformally Hamiltonian flows and conformally symplectic diffeomorphisms. So, what is conformally Hamiltonian flows? These are the flows that satisfy this relation with some non-zero constant eta. So if eta equal to 0, one obtains locally Hamiltonian flows. For non-zero eta, one obtains conformally Hamiltonian flows. For the phase flow map of these flows, we have this relation. So conformally Hamiltonian systems are in fact dissipative. What is interesting is that if the number of degrees of freedom is greater than 2, and the phase space is connected, then eta is automatically constant. And this can be proved very easily by these calculations. But if the number of degrees of freedom is 1, then actually each Hamiltonian flow is flow is conformally Hamiltonian if this eta is allowed to be non-constant. I will consider the conformally Hamiltonian flows according to this definition with constant quantity eta. Here you can see the conformal analog of the Hermann lemma. So if we have an invariant torus of a conformally Hamiltonian flow, and this torus carries conditionally periodic motions, then this torus is automatically isotropic, and in particular its dimension does not exceed the number of degrees of freedom. And here you can read a very easy proof. What is interesting is that in the case of conformally Hamiltonian flows, incommensurability of the frequencies is not needed, and the exactness of the symplectic form is not needed either. And what is also very important is that when the dimension of the torus is equal to the number of degrees of freedom, then such a torus is a repeller for positive eta and an attractor for negative eta. And the results looks as follows. So, in some phase space, and for a given vector omega, a Diophantine vector, one has a smooth n parameter family of vector fields. This external parameter ranges in some open domain of the n-dimensional Euclidean space. For some value of our parameter, one has an approximately invariant n torus with frequency vector omega, and some non-degeneracy condition holds. Then, for some value of the external parameter close to this initial value, one has a genuinely invariant n torus nearby with the same frequency vector omega. Actually, this is in fact a typical KM phenomenon for dissipative systems, that the flows are conformally Hamiltonian is not crucial. But in this paper, the proof of this theorem was obtained by the a posteriori method for conformally Hamiltonian flows. What is interesting is, of course, according to the general theory of hyperbolic invariant manifolds, an invariant torus, just as an invariant manifold, irrespective of the dynamics, exists nearby. I'm sorry. Exists nearby for any value of the external parameter close to this value. But the motion of this torus for an arbitrary value of the external parameter will not be conditionally periodic. And here actually we have an opportunity to recall Professor Anosov, the founder of the theory of hyperbolic dynamical systems and the chairman of the program committee of our conference, who is no longer with us, unfortunately. Actually, if one considers Hamiltonian flows, then very often one encounters some exactness conditions. For example, even in the definition of the Hamiltonian flows, this convolution should be exact. And in the Riemann lemma, for example, also the symplectic form should be exact. But if one considers conformally Hamiltonian flows, then no exactness is encountered in the definitions, in the proofs, and so on. So it suffices to have just this without any exactness. Okay, and here, probably this is my last slide. In this paper, one considers KM tori in presymplectic dynamical systems. So, what is a presymplectic two-form? This is a closed differential two-form with constant rank. If this form is not degenerate, then one speaks of a symplectic form. Otherwise, it is a presymplectic form. And in this paper, one constructs invariant tori by the a posteriori method for diffeomorphisms that conserve such presymplectic form. And also, I should like to mention this monograph, very recent, of this year, where the authors develop a complicated combination of KM theory and singularity theory, of KM theory within the a posteriori approach and singularity theory to study bifurcations of quasi-periodic invariant tori. These bifurcations occur in families of Hamiltonian flows or symplectomorphisms. Bifurcation points correspond to torsion degenerate, that is non-twist tori, and this theory is really impressive. So that's all for the a posteriori format, and this is actually the end of my talk. I have no time to speak about other results, and maybe this is even for the better, because all the other results in KM theory in the last decade are of much less importance, in my opinion, including my results. They are of much less importance than the a posteriori approach. No comparison. Of course, I mean only KM theory. Of course, there is a great and extremely important progress in Arnold diffusion, and we will attend the lecture by Kaloshin about this on Thursday. But Arnold diffusion is something orthogonal to the KM theory. In the KM theory, the most important thing is the a posteriori approach. I hope that all the remaining results will be available to the participants from the file of my talk. I hope that the file of my talk will be available to all the participants along with the files of the other talks. Okay? Thank you for your attention.
There is time for question, comment. Okay, mais it's not.
Sorry, what about?
Examples.
Yeah.
Okay, actually, examples of conformally Hamiltonian systems, there are a lot of examples, and these examples, for example, are presented in this paper and in other papers by the same authors. Unfortunately, I think that it would be difficult to write such examples just now, but there are a lot of examples and actually in many applications, actually. So this theory is really important for some branches of science. There are a lot of examples, but I think it would not be convenient to write them just now.
Okay. Maybe I have two questions which may be related. First, about the generalization to Gevrey space. Does it has any type of application also? And the second, you didn't mention the Nash-Moser theorem, which seems somewhere appear in the theory. So does it appear or it contributed?
Okay, according to the Gevrey systems.
Yeah. The Gevrey first.
Just a moment. You
mentioned extension to Gevrey. I know what a Gevrey is. Yeah, what they are.
You mean this?
Yeah. You said main achievement. Does it have more application than the classical case, than the analytic case?
No, I mean only here that these Whitney-Smooth families are not just infinitely differentiable. One can say something more.
Okay.
You see that actually, of course, there is a concept of Gevrey in, for example, in the theory of partial differential equations. Yeah. Yes, but I think that there is nothing in common with this. Here we have, here one only means that the derivatives,
I know.
yes, they don't grow very fast. And what is important is that for Gevrey functions, one has no uniqueness, of course. Yes, and that is why Whitney-Smooth families of invariant tori can be Gevrey. Okay. They cannot be analytic because otherwise they would be smooth, but they can be Gevrey.
Okay. And there is any relation with the Nash-Moser theorem and the CAM theory? Moving from analytic to...
Yes, yes. Nash-Moser theorem, it is used to prove finitely smooth versions of KM theorems. But you see, the traditional approach and this approach, both of them can use this Nash-Moser theorem. Both of them can be developed for finitely differentiable systems. In this point, there is no difference.
Okay, so super. We have on the program. We have to start at 1:05, which leaves us 10 minutes for break, and we come back. And we thank the speaker again.
Thank you. Никаких проблем.
Ну, на этом можно считать, что его нет.
Вообще через здание есть?
400. По всему зданию есть. Есть? А, у вас не собственный ноутбук, да? А, ну так входите. Конфет. Сеть конфет. Как это называется самое? Сеть.
Здесь можно попробовать? Оживить надо.
А4, Alt F4 нажал, и, видимо, это относилось ко всему нотебуку, а не только к приложению.
Попробовать. Это всегда лучше сначала попробовать, чтобы потом не мучиться во время доклада. Это не мое.
Этот мы закроем.
Да.
Этот мы мишка, куда-то делаем.
Я очень волновался, но ты не сможешь. Вчера. Я звонил, чтобы ты... Спасибо, забыл. Я такие вещи обычно не забываю.
Смотрите, пожалуйста, это вот этот слайд вперед, это слайд назад, а вот это это указочка. Вот выше, вот она.
Так, еще нужно бы это самое, мне посмотреть вот эту доску.
Какую хотите?
Может понадобится.
Параллельно.
Ну, потом.
class now. Okay, so I guess we should slowly start. You see our speaker is Professor Armen Sergeyev, and it will be about harmonic sphere and young meal, so I have the pleasure to welcome you.
Thank you very much.
You have upstairs.
So thank you. First of all, I would like to thank the organizers for the possibility to give a talk here. In most of the plenary talks during last Congress in Seoul, which closed up only 2 days ago, the speakers were proposing or discussing new and old unsolved problems, which are, by their opinion, will determine the direction of their field in next years. I think this is a very good tradition, probably going back to David Hilbert. And following this tradition, I would also decided to speak about some unsolved problem, which, in my opinion, is very important. This problem comes from mathematical physics and called harmonic spheres conjecture, and it relates two kind of objects which are here in the title, harmonic spheres and Yang-Mills fields, which seems to be quite different. Their definition is quite different and seems to be nothing to do with each other. But still, they are related, and this is the content of this conjecture. So in the beginning, I will speak about, I will present what is harmonic spheres and what are Yang-Mills fields. And then I will discuss later the conjecture. So let me start with, not with formal definition of, let me start with not with a formal definition of this harmonic maps, but from some model example also coming from theoretical physics. This is so-called SO3 model, which coming from ferromagnet theory, and it formulates like that. Suppose we have a Euclidean plane R2 in a three-dimensional Euclidean space. And suppose that at any point x of this plane, we have a unit vector phi of x, which depends smoothly on x. In other words, we have a mapping from this plane to the unit sphere in R3, which I denote by phi. We can define the energy of such a map by the usual way, by the Dirichlet type integral. Namely, this is the integral over the plane of the square modulus of the gradient. And we can look for the maps phi, which I just described, having finite energy, which are extremal with respect to this E of phi. From the finite energy condition, in fact, implies that such maps should stabilize at infinity. So taking at infinity some fixed value, which I denote by phi 0. And it means that such maps are extended to the compactification of our, one-point compactification of our Euclidean plane. And so we have a mapping phi from, in fact, from S2 to S2, from two-sphere to two-sphere. It is well known that such maps have topological invariant. Namely, this invariant called degree, and it can be defined as follows. We take the normalized volume form on the sphere S2 in the image, then pull back with phi to this S2 here, and integrate with respect to R2. This is well-known invariant degree of the map. Okay, now let's try to solve this problem, which seems quite simple, but I think it's worth of considering. Since we are in the two-dimensional case, it's very natural to introduce complex coordinates. And we introduce a complex coordinate z, which is x1 plus ix2, in the definition domain of our phi. This is R2 plane. And in the image, in the S2 in the image, we introduce stereographic complex coordinate. That means that it's defined everywhere except for the north pole. Then if we rewrite the formulas for the energy in degree in this complex coordinate z and w, we will obtain very remarkable formulas. Namely, the energy is this integral, where in the denominator we have just a square, the sum, the square of d and d bar derivatives of w. And in the denominator, we have just usual conformal factor because we are sitting on a sphere. And what is remarkable that the degree is given almost by the same formula. Well, I don't pay attention to these coefficients, but in the denominator here was plus and here is minus. That's the only difference between these two formulas. So we can compare energy and degree. And we arrive immediately at this inequality, that the energy is always greater than, for pi, modulus of degree, phi. Moreover, the equality here in this inequality, the equality here is attained. You can see here the formula. So when it is equal, when, for example, when it is zero, this zero, so the map is holomorphic. So equality for degree, positive degrees, is attained only on holomorphic functions, and for degree negative, only on anti-holomorphic functions, W of z. So we have already local minima in our problem. In fact, it can be proved that the functional E of phi has no other critical points except for this local minima. This is a very strange phenomenon, but it happens sometimes that local minima exist, but no critical points. Having this description, it's very easy to get a more explicit description. To describe all local minima of E of phi, we set this limiting value of phi equal to 1 using SO3 invariance of the problem. SO3 invariance of the problem. That's why this model is called SO3 model. And then, assuming that for simplicity that degree is positive, we deduce that all minima of E of phi with fixed degree k are given just by rational functions. So all minima are given by these rational functions with aj and bj arbitrary complex numbers not equal to each other. So you see, it's a very simple problem, but it's already quite interesting. We will call now the maps from R2 to S2, which are extremal for the energy functional. We will call harmonic. And in fact, what we have proved, just reformulating what we have proved that all harmonic maps, sorry, here should be P1. Now I will denote sphere S2 as P1, just to underline that this is we consider it as a complex manifold. So the Riemann sphere, so all harmonic maps from Riemann sphere to Riemann sphere are given either by holomorphic or by anti-holomorphic maps, and there are no other harmonic maps. By generalizing this simple example, we can come to a general definition of harmonic maps. Namely, we shall consider the maps from the Riemann sphere to Arieyan to Riemannian manifolds N, and we call such a map, a smooth map, of course, and we call such a map harmonic if it is extremal with respect to the energy functional, which is again given by Dirichlet integral, though instead of square modulus of d phi, we have here square modulus computed in the metric of this manifold n. That's the only difference. Okay, of course, we can write, immediately we can write equations for the critical points. This will be Euler-Lagrange equations. And in fact, they will look, I do not give precise formulas because I will not use them, but they look like Laplacian equations, a system of equations for Laplacian, but which are nonlinear because of the non-flatness of this n. These are nonlinear Laplacian equations. If the manifold n is scalar, that means that n has, apart from the metric, it has also complex structure, which is compatible with Riemannian metric. Then it can be proved, this is Lichnerovich theorem, well known, that holomorphic and anti-holomorphic maps again realize local minimum of this energy functional, as in the previous example. But in general I mean if the dimension of n, complex dimension, is greater than 1. Usually there exist non-minimal critical points, so harmonic maps which are neither holomorphic nor anti-holomorphic. And that's our problem. We want to describe such maps. So I have introduced the first object as harmonic spheres in Riemannian manifolds. Now I have to introduce the counterpart of it, namely Young-Mills fields and instantons. Let me recall you the definition. We denote by G some compactly group you can think of just group SU2, 2 by 2 unitary matrices. It's already quite sufficient for the future. And we consider a connection, G connection on R4. In physical terms, is gauge potential. If you don't like such words, just think of one form of this type, where coefficients are smooth functions with values in the Lie algebra of our group G. So if the group G is SU2, then these coefficients are just matrix functions with skew Hermitian matrix values. Next, we take the curvature of this A, or in physics terminology, this is gauge field. And it is given by the 2 form of this type, where f mu is just derivative of this A. So d mu a nu, d mu is this. D mu a nu minus d nu a mu. And here we take commutator of these functions, commutator in the corresponding Lie algebra, or if you think about matrix functions, this is just usual matrix commutator. With all these definitions, we can introduce our main object, namely action functional. Young-Mills action functional is introduced like that. This is integral over the whole space, R4. This is Euclidean analog, of course, of space-time. We take the curvature, this FA, this is to form, as I already said. And we take star of FA. Star of FA, it's a Hodge operator. It associates with some form, the complementary form to the whole volume form. So in this case, this is also to form. So we multiply these two matrix two forms, and we take the trace. Trace with respect to some fixed invariant interproduct on Lie algebra, or in matrix case, this is just matrix trace. So what we get, we have a 4 form, but already scalar 4 form, and we can integrate it. This is what is called Young-Mills action functional. This is our main object. What is non-trivial with this functional? Non-trivial is that this functional is invariant under a huge group of transformations. This makes the whole situation non-trivial. Namely, it is invariant under gauge transformation given by this formula, where G is some smooth map to a group G, and G acts on its Lie algebra with respect by a joint representation. Or if you think about matrices, this is just usual differentiation of matrices and multiplication of matrices. So our functional is in fact invariant under this huge infinite dimensional group. So from this invariance, it follows that in fact S of A doesn't depend on A, but rather on A modulo these gauge transformations. So we are not interested in describing, first definition. We shall call gauge fields, these gauge fields FA, which are extremal for this functional, action functional, and have final action, we call Young-Mills fields. And our main problem is to describe all these fields. But in fact, we are not interested in describing all these fields because of this invariance. So in fact, we are interested in describing the solutions of the corresponding Euler-Lagrange equations only modulo gauge transformations, because gauge transformation do not change the physics of the problem. So we are interested in what is called moduli space of solutions of these equations. These equations are also very non-trivial matrix, non-linear equations, very unpleasant and hard to solve. Okay, so we are interested in description of these moduli spaces. Young-Mills fields, as I already said about harmonic maps, they also have integer value topological invariant. This topological invariant is called by topological charge. And in fact, the formula is very similar to the harmonic case. You remember that in harmonic case, we had here star, Hodge operator. So it was volume form. But now we have almost the same formula, but no star here, no star here. And it may be proved that modulo this constant AP squared, this is an integer. Of course, it's not easy to prove, but it can be proved. Again, if we compare these two formulas, this formula and this formula, we immediately arrive at, oh, sorry, we immediately, no, wait a moment, just, wait a moment. I am a little bit hurry. We have here topological invariant, and we have here this, this functional. So I want to do now something which we did already for harmonic maps. Namely, I write down this, this gauge field as the sum of so-called self-dual and anti-self-dual, which are defined by this formula. The star is hot star here. Of course, this is just formal transformations. And if this was the solution of Euler-Lagrange equations, this shouldn't be the solutions a priori. But it's very convenient to use this notation, because in this notation, the Young-Mills action is written in this way. So this sum of square modulus, where the square modulus is computed with the help of invariant inner product, or just usual matrix norm. And K of A is given almost by the same formula, except for this minus here and here plus. So again, we can compare these two formulas with each other, and we immediately arrive on this inequality, that a Young-Mills action is always greater than the modulus of this topological invariant. Moreover, again, as in the previous case, as in harmonic case, we can see that equality here can be attained for K positive only on solutions of these equations, and for K negative, only on solutions of these equations, which are called self-duality equations. So now I can give another definition which is related to Young-Mills theory, namely solutions of the first equation with finite action are called instantons, by the reason which I unfortunately have no time to discuss. And solutions of the second equations are called, also with finite action, are called anti-instantons. And as I explained, they are local minima of our functional. So instantons and anti-instantons realize local minima of this action functional. But up to some point, it was believed that there are no other critical points. But of course, now it's constructed many examples, which shows that non-minimal critical points also exist. And one of our tasks, and I think it's a very good problem, to describe this non-minimal critical points, which is still not done. But let me just say that if we compare formally compare harmonic maps with Young-Mills fields, we notice immediately an evident analogy between holomorphic maps and instantons on one side, and harmonic maps and Young-Mills fields on the other side. Very similar. So physicists, of course, noticed this long ago, this evident analogy, but so they believe that there should be some relation between them. And this relation really exists, as I will show later. So there is a deep connection between these quite different objects. Okay, now the problem which I will consider, and the idea how to prove it, we have already idea how to solve this problem, is based on the Twister interpretation of both of this object. I will say a little bit later why it is so important to have this Twister description. But let me just formulate. First, I formulate Twister description of instantons and Young-Mills fields. What is that? I recall that Young-Mills fields are some forms, matrix-valued forms, defined on R4. So what we shall do, we now compactify this R4 to S4 by 1 point, and identify S4 with quaternion projective line, HP1. In the same way as a Riemann sphere is identified with complex projective line, absolutely in the same way. Why I want to do this? Because I want to construct some, what is called Twister bundle over R4, basic Twister bundle. And now I will describe this. So what is a quaternion projective line? It is defined absolutely in the same way as a complex projective line. So points of quaternion projective line are pairs of quaternions. I write quaternions in complex way. So Z1 and Z2 are just usual complex numbers. And J is another imaginary unit which anti-commute with I. So we write the points of A as pairs of quaternions. not equal to 0 simultaneously, which are defined up to multiplication by non-zero quaternion, just precisely as for complex numbers. Only we should fix from which side we should multiply, because its quaternions are non-commutative. So we fix, for example, from the right. We multiply from the right. Then the twistor bundle, which is the bundle of three-dimensional complex projective space over this quaternion projective line, in these terms is defined very easily. This is a tautological formula. So a point of CP3 is a four-tuple of complex numbers, which is defined up to multiplication by a non-zero complex number. And this is, as I said already, this is a pair of quaternions, which is defined up to multiplication by a non-zero quaternion. And the formula is just like that, tautological formula. So it's very simple description of this bundle. But because this equivalence is different here and here, we get that there is a fiber of this map. And the fiber is precisely a complex projective line or a Riemann sphere, as you like. So this is a twistor bundle. So now I will omit this C, because there will be no quaternions later on. So P3 is always CP3 and P1 is always CP1. So we have defined this twistor bundle over S4, and now we can restrict it to our R4, on which our potentials are given. For that, we should just throw away from this the fiber over a point at infinity, which I denoted by like that. So this is our basic, yes? Bracket means that this four tuple is defined up to multiplication by a non-zero complex number. So if you multiply, this is the same. And here, brackets, sense is different. Here is defined up to multiplication by quaternion from the right. So that's, sorry, I haven't explained this. So this is what is called a basic twistor bundle, and we will use it for the twistor description of instantons in a moment. But let me say that twistors were introduced by Penrose, but a big deal was done by the paper of Atiyah, Hitch, and Zinger, in which they, in fact, interpret the fiber of this twistor bundle, so this is Riemann sphere, was interpreted by them as the space of complex structures on the tangent space at this point, which are compatible with metric orientation. So complex structures is just linear operators with square minus 1, and that was interpretation of Atiyah, Hitch, and Zinger of this twistor bundle, and we will use it later. Okay, so now we have constructed a twistor bundle over our R4, and we want to describe the modular space of G instantons. That is the quotient of the space of all G instantons modular gauge transformations. And it was discovered by Atiyah and Ward, the theorem. It's a twistor description of this modular space of this instanton. So according to Atiyah Ward, this is the space of equivalence classes of holomorphic bundles over P3, which are holomorphically trivial on all fibers. So what we have here, we have here R4, we have here R4, we have here P3, and we have here some connection and the curvature FA defined on R4, and we pull it back using this pi, we pull it back to something here. And it turns out that what we get here above, this will be not just a connection, but a complex structure. So it means we started with some equations on R4, we pulled them back, and we got no equations. That's holomorphic geometry. This is something similar to, this is usual feature of this twistor theory. It's similar to Einstein gravitation theory. According to Einstein, we know that if we introduce the natural metric defined by masses, then equations disappear, only kinematic stays. We have only kinematics. Here, the same. We had some equations, conformally invariant on R4. We pull them back to the twistor space, and on the twistor space, we have only holomorphic geometry, no equations in some sense. So this is the idea of twistor theory. Yes, this I have described already. And it's very remarkable that this result has the following two-dimensional reduction, which is due to Donaldson. Namely, we can substitute here P3 by some two-dimensional space, namely the direct product of two Riemann spheres. And then this modular space will be the equivalence classes of holomorphic bundles over this direct product of two spheres, which are holomorphically trivial on the union of two spheres at infinity. So that's all what remains from this triviality on pi fibers remains only on two triviality on two crosses, on cross of the two projective lines. Unfortunately, the proof is not like that. So you just deduce from that the proof is completely independent. It cannot get it just by reduction. Sorry. Okay, now I explained the twistor interpretation of, maybe just one word. There is a similar description of the modular space of Young-Mills fields on R4, which is due to Eisenberg, Green, Yaskin, Witten, and Manin. This is very similar to this description, but only the pullback of this Young-Mills fields will be some bundles over P3 times P3 dual. And this will be some, with some triviality condition, which is similar to that. Sorry, I cannot describe it because it's a little bit too hard to describe it shortly. Just have in mind. So the next point is twistor interpretation of harmonic spheres. For harmonic spheres, we also have twistor interpretation, and also very interesting. Namely, we shall use interpretation due to Atiyah, Hitchin, and Zinger of this twistor bundle as the bundle of complex structures on S4. Using this definition, we can extend it to any even-dimensional Riemannian manifold. Namely, the twistor bundle over such an oriented Riemannian manifold N. This is the space Z with projection. Such that the fiber at X is given by the space of complex structures on the tangent space, which is compatible with metric orientation. This is completely similar to description in the case of R4. This twistor space, and that was the main discovery of Atiyah, Hitchin, and Zinger, that this twistor space Z has in fact a canonical almost complex structure, a natural almost complex structure, which I denote by J1. It's usually it's not integrable. It's integrable only if the manifold N is conformally flat. But still, let me stop for a moment. So we started from some Riemannian manifold. On Riemannian manifold, probably we have no complex structure at all. Then we consider all complex structures in the points, at the points. So we have this bundle, twistor bundle, and this bundle has no complex structure. So you see, it gives an idea how you can reduce the problems of real geometry to complex geometry. Just pull back to the twistor space. That was the main idea of Penrose. Okay, oh, sorry. So idea is to use this Penrose program, how it is called, to describe harmonic maps. So what we have here, we have our manifold N. We have a map, harmonic map, from P1 to N. And we want to use a twistor description. We have here twistor bundle Z. So what's the idea? The idea is very natural. How we should reduce everything to holomorphic case? There should be some holomorphic map psi, or almost holomorphic because it's non-integrable structure, such that the projection gives us, the projection of it gives us the original map. And this is almost true, but not precisely. Namely, if we do this, then we will see that the projection will be a solution of second-order nonlinear equation, but with the wrong signature. The signature will be not like we want to have for Laplace, 2n, 0, but it will be n point n, so wrong signature. So if we want to use this Penrose description for our case, we should change the almost complex structure, which was defined by Atiyah, Hitchin, Zinger. And in fact, it was done by Eels and Salomon. And the structure is the following. We consider the new structure was equal to J1 in the direction which are tangent to, which are horizontal with respect to Levi-Civita connection, and to minus G1 in vertical directions. Sorry? Sorry? Non-integrable, it means the following. Sorry, I don't give all definitions. But integrable, it means that if you apply 2 times Cauchy-Riemann operator, you should get 0. So the square of Cauchy-Riemann operator should be 0. And this is precisely only for integrable complex structure. If it is non-zero, this means that it's non-integrable. So almost holomorphic structure differs from the complex structure only by this condition. That should be trivial. The square of Cauchy-Riemann operator should be trivial. Unfortunately, it's not always like that. But this very strange complex structure, which is always non-integrable, in fact, always non-integrable. And I can explain why, because in some directions it should be holomorphic in the usual sense, but in other directions it should be anti-holomorphic. So it's a very strange complex structure. So it's not surprising that it's non-integrable. But there is a theorem proved by Ilse and Salomon that projections of such maps, holomorphic with respect to this strange structure, are harmonic. So we got what we wanted. But from the first view, it seems disappointing, because what we got, we replaced one problem, which was for, well, nonlinear but differential equations. We reduced it to the problem of constructing holomorphic spheres, almost holomorphic spheres, but with respect to non-integrable structure. And these non-integrable structures may be quite bizarre. For example, it may have even locally, no non-constant holomorphic functions. So they may be quite bizarre, and it seems at the beginning that we are not very successful. But that's the wrong impression, because we consider not functions, but the dual object. That was the idea of Gromov, that on non-integrable, almost complex manifolds, you shouldn't consider functions, because probably you don't have them. You should consider the curves. And that was the idea. So we consider the curves, holomorphic with respect to this strange non-integrable holomorphic structure. But what does it mean that it's holomorphic? It means that they are solutions of d bar j equation on the Riemann sphere, where j is just a pulled back almost complex structure. So this is already equation on the complex plane, which is of course integrable. The complex structure is integrable. So you should solve some Cauchy-Riemann equation on nonlinear, but on a complex plane. That was the main idea, so to say. In particular, such an equation has many local solutions. That was the original idea of Gromov, and it's quite important here. So that's how we proceed. So, in fact, what we have done, we have reduced the original problem, which was a second-order differential equation. We reduced to the first-order differential equation, also nonlinear, but this is first-order. It's quite different. So we succeeded in some things. And in fact, how much time I have? Sorry. Ten minutes more. Okay. So probably I will skip this. I wanted to give you a description of harmonic spheres in complex Grassmannian manifolds using this twistor approach, but probably I will skip it. I only say that in case of this Grassmannian manifold, this twistor bundle can be described explicitly, and this is well-known manifold. This is Fleck manifold. So Fleck manifolds are twistor spaces for Grassmann manifolds. So, but I should skip. Here we have a complete description. So this is complete description of this twistor. Interpretation gives the complete description. Now I come to my original problem. My original problem was to relate Young-Mills fields and instantons relate to harmonic maps. And this is really so, but we should consider harmonic maps, harmonic spheres, not in finite dimensional, but infinite dimensional manifolds. And the role of this infinite dimensional manifold will be played by loop space. The loop spaces of the Lie group J is the following. You consider the group of all smooth maps from the circle to this group, and you divide by constant maps. This is what is called loop space. This space, in fact, is very good space. In fact, it is Keller manifold. It means that it has a Riemannian structure and has a compatible complex structure, but again, I will not explain this to save my time. So now, what is the description? Let me first give you the Atiyah theorem, which relates instantons with holomorphic spheres. So I recall that there is a Donaldson theorem which says that the moduli space of G instantons on R4 are the same as holomorphic bundles over P1 times P1, which are holomorphically trivial on this coordinate cross. Atiyah theorem gives an interpretation of the right-hand side in terms of the holomorphic spheres. Namely, this theorem asserts that these holomorphic bundles over P1 times P1 is just holomorphic spheres in this loop space. Very simple description. In fact, the idea of the proof is very transparent, but I should skip it because, yeah. So if we combine the Donaldson and Atiyah theorems, then what we get? That there is one-to-one correspondence between moduli space of G instantons on R4 and holomorphic spheres in omega J. Here the term base means that the infinity goes to a fixed point here in omega J. So this is Atiyah theorem. It is already quite surprising. I know that it was quite surprising for physicists because this is completely different object. One object is this G instantons on R4, and the other object is just holomorphic mappings to the loop group. It shows that this is the same. This is the same, in fact, because there is a direct correspondence between them. There is a direct map. So, in fact, what we have here, let's look again on this. We have here, in fact, correspondence between local minima of two functionals. Here, instantons are local minima for the Young-Mills actions, as I explained before. And here on the right-hand side, holomorphic spheres are local minima of the energy functional. So we have correspondence, one-to-one correspondence between local minima of two different functionals. So now, if we replace here the local minima by the critical points, we arrived on this harmonic spheres conjecture, which asserts that it should exist one-to-one correspondence between moduli space of Young-Mills fields. That means not local minima, but critical points of Young-Mills functional, and based harmonic spheres in omega J. So this is the conjecture, which still not proved. And I will explain to you a little bit later why it is so important. First of all, we can look of this procedure switching from local minima to critical points as a kind of realification procedure. Namely, if we substitute here these maps just by holomorphic functions from P1 to P1, or from C to C, then the switching from holomorphic and anti-holomorphic functions to arbitrary harmonic functions is trivial, because any harmonic function on the complex plane is just the sum of holomorphic and anti-holomorphic map. So we are doing the same, but for different functional. We are doing the same for the energy functional. And here the Euler-Lagrange equations will be non-trivial, non-linear, but still it's kind of realification, non-linear realification procedure. Okay, now what about the proof of this conjecture? Why we cannot prove it? Unfortunately, direct generalization of the proof of Atiyah-Donaldson theorem to harmonic is not possible, since the proofs of Donaldson theorem is purely holomorphic and doesn't extend to harmonic case. That's the main problem. Atiyah theorem extends easily. So at some point I didn't know what to do in this situation until I understood that we should try to reduce everything to holomorphic case, again using this twister construction. So we have here two objects. We have here Young-Mills fields. We have here harmonic spheres, and we want to prove that this is the same. So what we do, we go to twister space. This is twister description. And this is twister description. So twister description in the first case was obtained by, as I said, by Manin, Eisenberg, Green, Yaskin, Witten construction. Namely, Namely, this twistor space is described in terms of P3 times P3 star. And here, this description was obtained by me and my student, Yulia Belashapka, and this description is like that. This, again, this holomorphic spheres in some flag manifolds, which are called virtual because this is infinite dimensional case. Sorry, I had no time to speak about them. But there is some description in flag manifolds, yeah. So the idea, if we now, instead of proving this conjecture here, we just pull back here and prove this conjecture, because this is already holomorphic. That should be, according to general twistor philosophy, it should be holomorphic assertion. And for holomorphic case, we have already. So that's the idea. Unfortunately, up to now, I was not able to realize this idea. And the problem is that description of Manin and others for the Yang-Mills fields is quite different, using different language than here. Because here you see they are using dual space, but while we do not use dual space. So I think that the first step should be to obtain description in the same terms. And that's what we are trying to do now. And then try to describe this, to prove that. So I will skip this. This is description of twistor bundle, but I have no time to describe it. So now let me finish this, why we are so interested in this conjecture, why we are trying so hard to prove it. Suppose we have proved it, then what it will give for description of Yang-Mills fields. You know, up to now, this problem is not solved. We have a very good description of instantons due to Atiyah, Drinfeld, Hitchin, Manin. It's quite explicit description. But we have no description of Yang-Mills fields, and nobody knows how many of them. If we throw away instantons and anti-instantons, how many remains? So if we prove this conjecture, then from this conjecture, it will follow the following description of Yang-Mills fields, that any Yang-Mills fields can be obtained starting from some trivial one, some trivial solution by kind of dressing procedure, kind of background transformations. So for which we use instantons and anti-instantons. So we should somehow sum up them. It will follow because we have already, here we have the description of this part. So if we succeed in proving this description, that will mean that there are many more Yang-Mills fields compared to instantons and anti-instantons. Just very opposite to our original conjecture that there are no other critical points apart from instantons and anti-instantons. So I hope that this is true, and I should say that the two-dimensional analog of this is proved already. That was proved by Friedrich and Hindermann. I think I'm not sure in the second name. By Thomas Friedrich and his colleague, the two-dimensional analog is true of this conjecture, but four-dimensional, of course, is quite different. So it's not the proof. But this is some evidence that the conjecture should be true. Thank you very much. Конечно.
Ваша информация ограничивается каким годом библиографических ссылок?
What is the boundary for the year of your bibliography?
Well, of course, I have.
Дайте-ка по-русски ответьте мне.
Да, конечно, у меня есть библиография, я могу вам ее предоставить. У меня даже есть книжка на этот счет.
Последний год какой у вас?
Последний год 2014.
Спасибо.
The last year is this year.
Background transformations.
Yes.
What is on the harmonic field part? What kind of transformation do you have there? And next question, I'm educated by calculus of variation. If you ask for on the harmonic side, I would immediately, not looking at anyone else, I would go to try to do some more theory approach like in order to find the other critical points. Why do you reject that?
To describe these harmonic maps, you will use.
For me, because I was educated like that,
Yes.
and also studied a lot of minimal surface, and there's infinite dimensional Moore theory in order to catch the others. But this seems to be not the correct approach. This I would like to understand why.
The approach here is, you see, the main problem is that you consider harmonic maps with values in curved manifold. And this makes the problem quite different, because, for example, it's not the solution of Laplace equations, it's solutions of nonlinear Laplace equations. Yeah, of course you know this.
It's problem of deformation then in the correspondence.
I don't know. I don't think that Morse theory will succeed here.
Yes, I can feel it, that maybe you have the advantage, you have these conformal structures which are off from that, but...
I can tell you that the first, the physicists started to work on this problem, and many famous physicists, for example, Weinberg was working on this problem, and they considered the mappings from Riemann sphere to projective space. And they produced precise, very explicit construction, like Backlund transformation. So you use the function, you use the oscillating curve for that, and you use orthogonal complements. So procedure is very, very easy for CPN. So this is just idea coming from the CPN. This is just another formulation of this original procedure found by physicists.
But this new solution which you get, do they have some topological description? Because we somehow have here otherwise a degree.
Description is quite explicit. We have this Backlund transformation, which was found by
the parameters of the Backlund.
Yeah. Well, this description does not say you much about parameters, because you have different Backlund transformation, and for different chains you might have the same result. So it doesn't give you the parameters; it gives you the way of constructing. Unfortunately, it doesn't help if you want to construct the whole.
I want to give them characteristics to somehow to mark them not just by their degree, because they are mapping as maps.
This energy. There is energy.
You take the energy.
And energy is decreasing when you use this Backlund transformation. Energy is the main parameter, of course.
You take the energy.
You take the energy.
Several of the same energy.
Yeah, and then you decrease the energy. This is mainly due for to Uhlenbeck and Welle. Thank you very much.
Okay, we have a lunch break and we will continue at 3:30.
Russian mathematician Stanislav Pokhozaev. The first speaker is Professor Nazarov. The title of his talk is The Brazis-Nirenberg Effect for Fractional Laplacians.
All right? Do you hear me? Thank you for the introduction. It's a great honor for me to open this memorial session. I'm not sure that it was a right choice because I am not a student of Stanislav Ivanich and I'm not a collaborator of him, but nevertheless, here is the title of my talk. It is based on joint work with Roberto Mussina, who is also here, and it is available in Arxiv, and now it is accepted to publication in Revista Mathematica Iberoamericana. Stanislav Ivanich is a well-known mathematician, and he is many of his results are known, but I think that everybody in nonlinear PDEs knows just this small paper of Pokhozaev of 65, where he was very young. This is taken from Central Blood, the review of this talk, and this was, excuse me, a review of this paper, and just here the well-known Pokhozaev identity was introduced and applied for the result of non-existence, and the non-existence of solutions, it was maybe the main topic of his works for all the time. The picture which I, and other pictures which I show you are taken from a large collection of Gennady Anatolyevich Kalябin. Here is Stanislav Ivanich at the time of his talk at the conference in Cortona in Italy. And as I said, I did not collaborate with Stanislav Ivanich, and I met him in some conference, and first of all at seminars. And I can say that the seminar was, he was in his own element, the seminars. And here is a picture from seminar in Mathematical Institute, in Steklov Institute, and you can see here Alexander Leonidovich Skubachevsky and Vladimir Dmitrich Stepanov with Stanislav Ivanich. And I can say that this his fistier manner at the time of seminar, it was and it is unforgettable. I think that to give a talk at seminar where Stanislav Ivanovich was present, it was always a challenge for the speaker. He was always pointed to the speaker, and you can see some pictures from seminar. All these pictures are just from the Бесов, Никольский, Кудрявцев, Похожаев seminar, well known on function theory and nonlinear PDEs in Steklov. Quite often position. And this Mephisto smile also very nice. And this one. And here is Stanislav Ivanovich after the seminar. I can say that after Vladimir Alexandrovich Kondratiev passed away, for me the nonlinear PDEs in Moscow were associated with the name of Stanislav Ivanovich. And I can say that these two deaths, Kondratiev and Pokhazaev, are personally and professionally a tragedy for me. Now let me turn to my talk. Let's take two real numbers. N is the dimension. Here you can see that omega is domain in Rn, and we suppose that the origin belongs to omega, and we take two real numbers with this restriction. I define the critical Sobolev embedding exponent. This exists due to this inequality. And I study these two equations. You see that here is just fractional Laplacian of arbitrary real order M. And here you can see the critical term, and here you take some perturbation, lower order perturbation. S is smaller than M. We consider two types of perturbation. Surely they coincide when S is equal to 0. And lambda is a parameter. Let's consider the simplest case when S is 0 and M is 1. Then we obtain a well-known equation, and the Dirichlet condition in this case is just as follows. Just by Pokhazaev's work, which I mentioned, this boundary value problem has no positive solutions for at least in some domains, in star-shaped domains, for lambda smaller or equal than 0. But in 1983, Brezis and Nirenberg proved a very interesting fact that if lambda is greater than 0, we can obtain the positive solution and in arbitrary domain. So we can see that lower order perturbation can change this situation of non-existence. But for n is greater or equal than 4, the existence arises for arbitrary small positive lambda. And for n equal to 3, at least for the ball, non-existence for lambda small enough and existence for larger lambda. For the ball, they discovered just sharp value of lambda, the border between these areas. And we say that the dimension n3 is critical for this problem. I note that this effect is a nonlinear analog of well-known zero-energy resonance in linear theory of the Schrödinger operators. We consider the case of arbitrary S non-necessary 0, and we can hope that as larger is S, as stronger is the effect of low order perturbation. And this is really the case. Here is our main result. We take M and let S be as follows. Then N is not a critical dimension. This means that the corresponding problems for both equations, they do not differ in this sense. We have a solution for ground state solution for arbitrary small positive lambda. Here you can see some particular case. We had some previous, we knew some previous results. They are mostly for S equal to 0. For arbitrary natural n, the very interesting result of Pucci and Serin. And then some generalization. You can see here many papers which investigated this case. Then for M between 0 and 1, and also for S equal to 0. And the only work for S not 0, S1 and M2, the paper of Calderoli and Mussina. And also the so-called for the so-called Navier boundary conditions, also just as this S equal to 0 and M between 0 and 1, it is another problem. And in the talk of Roberta a bit later, she will explain the difference between these two type of fractional order Laplacians. This corresponding problem was investigated in these two papers. This one is for M equal to 1/2, and this one is for arbitrary M between 0 and 1. For this type of fractional Laplacians, the case of arbitrary M is still open problem. Now I explain what I mean when I say the Dirichlet Laplacian, fractional Dirichlet Laplacian. It is defined on the smooth compactly supported function just by the Fourier transform. And its quadratic form is as follows. And we say Dirichlet Laplacian simply in omega, simply having in mind this operator on functions supported in omega bar. And moreover, it's well known that if M is between 0 and 1, this operator can be considered as integral super singular operator. Let's denote by dm the Hilbert space with this norm. And this is a well-defined space just by this Sobolev inequality, which is true if M is less than n half. This sharp constant, the best Sobolev constant, is now well known for arbitrary M, for arbitrary real M less than n half. By this paper, for M equal to 1, it is surely well known from the middle of 70th. And it is this constant is attained in this space by these functions and also its translations and dilations. Here is the natural space in which we will consider our problem. We consider the weak solutions, which in usual variational sense, this is just what I explained a bit earlier, that we consider the operator in Rn, but defined on the space of function, subspace of functions supported in omega bar. And in this, the quadratic form of fractional Dirichlet Laplacian is well defined on this space. And we can, here you can see the explanation that if M is integer number, then you obtain just the Dirichlet boundary condition in standard sense. And we consider the following functionals. And it is easy to see that corresponding, the critical points of corresponding functionals after proper normalization are just the solutions of considered problems. Yeah. These functionals are well defined in this space without zero. And we should prove that this functional has a critical point. These functionals have critical points, but really we prove that they have ground states. The technical lemma, which is more or less standard now, is the first is trivial because we subtract something that this quantity is less or equal to the sharp Sobolev constant. Then, if it is equal to the sharp Sobolev constant, then this infimum is not achieved, just because this infimum is achieved only on a function with non-compact support. And if it is less, but strictly positive, but strictly less than the sharp Sobolev constant, then it is achieved. And the same is true for the second infimum. And now, really, all is very simple. We should simply take a proper trial function and then simply to calculate sufficiently sharp calculations. And we choose this trial function as you see, the function which minimizes the Sobolev quotient, we shrink it by epsilon. And then we multiply it by cutoff. Here is some cutoff. And normalize. And then it remains to calculate. Here is the result of calculations, but you don't need to read it carefully, but the result is as follows. That if we push epsilon to 0, then corresponding functionals can be estimated by this quantity in the limit we obtain just the Sobolev constant minus something, and you can see here lambda, and here also is lambda. So if lambda is positive and epsilon is sufficiently small, you can obtain the result under the threshold. Lower this functional is strictly less than Sm. And by lemma, this functional has a ground state. I write it here for the first functional, but for the second, it's the same. As I said, this is true for S greater or equal to 2m minus n half. Let's look here. If m is 1 and S is 0, then just for n for n greater, we have non-critical dimensions, just as Brézis and Nirenberg established. And for n equal 3, we have critical dimension. In the general case, we conjecture that the result is the same. We conjecture that for sufficiently small positive lambda, for example, if omega is a ball, that for sufficiently small positive lambda, we have no positive solution. And for greater lambda, we have positive solutions. Now we can prove only the first statement, the second statement, which is surely the simplest part. And generally speaking, this problem is open. This is all. Thank you for your attention. Yeah, it's just the Navier case, and the result will be the same, but it is in progress now. It will be the same, but a bit later. Yeah, it will. I say it will be the same. Yeah, it's a philosophical problem. It is the same just now when we did not prove it yet, but or no.
Some more questions or comments? So let's thank the speaker again. Could you please show some more photos of Professor Pokhozaev?
Так, сейчас. Это, конечно, давай. Нет, вот сюда, вот вперед. Вот, взял. Так, ладно.
View, sunlight view.
That's what means view. Yes, and here.
This Control R. You can put Control R.
That's fantastic. This picture, and to go out this.
Yes, escape. Control R.
That's fantastic.
Okay. I will take my. Моя вот.
We'll try.
So the next speaker is Professor Musina, and the title of the talk is Two Fractional Laplacians.
I will take this, but I hope I will not use. Okay. Good afternoon again. I will try to avoid the use of microphone, but if you don't hear me well, please let me know. I will use it. So of course I want to thank the organizers for having given me the opportunity to have a talk in this great conference, and in particular to have give a talk in this section dedicated to Pojaev. I also have somewhere, I don't know where, a picture, but it seems I've lost it. Because I had the occasion to meet Professor Pojaev several times, because he often went to visit our universities, the University of Trieste, of Udine, and SISA in Trieste. And in particular, he was used to come in Trieste to visit his collaborator and great friend, Enzo Mitidieri. So I think I'm very lucky because of that. So I will talk about a couple of papers in collaboration with Alexander Nazarov, Steklov Mathematical Department. And of course, this talk is dedicated especially to Professor Pojaev. I will be concerned with a fractional Laplacian operator of any real positive order M here. And as Nazarov said before, the Dirichlet, the Laplace operator of order M is defined for, say, a smooth and compactly supported function U through the Fourier transform. Once you have this notion, you introduce in a standard way the Sobolev space HM over N, those maps in L2 whose Laplacian of order M half is in L2 itself. Now we take a bounded and smooth domain omega, starting from now, omega will always denote a bounded and smooth domain. We take the functions in Hm over n, whose support is contained in omega. We call this space H tilde m, and we endow this space with the natural, its natural norm, which is the Gallardo-Nirenberg norm in Hm. Actually, this turns to be an equivalent norm on H tilde of m. And so we have a nice operator and a nice space, Dirichlet, and a nice Dirichlet norm. But also, one can define the Navier or the spectral, if you want, Laplacian of order m, exactly as the nth power of the standard Laplace operator on omega with homogeneous Dirichlet boundary conditions. It means that you have to introduce the eigenvalues, the eigenvectors of minus Laplacians on H10, and you formally define this Laplacian of order m. We will call it n distributional in this setting, the nth order Navier Laplacian of the function u. Then we introduce the domain of the quadratic form that one can associate to this m Laplacian. We call this space Hm of n in red. And we endow this space with this norm. It turns out that we have obtained a nice Hilbert space. Those two fractional Laplacians have been largely studied, and in particular in the recent year, because in recent year there has been a great development in studying equations, differential equations governed by fractional and more generally non-local differential operator. The reason is because, for instance, several those non-local differential operators model situations in which you have to take into account long-range interactions. They are not defined through pointwise definition, but through, say, some integrals, so they can better describe long-range interactions. And the Dirichlet and Navier Laplacian are, say, among the most largely studied, perhaps, fractional differential operators. And so we want to compare them. And to compare them, first of all, we have to understand which is the relation between the domains of the Dirichlet norm, that is this H tilde, and the domain of the Navier norm, that is this H mn of omega. The answer is already known. It can be found after checking a little bit in Tribel's book, in Tribel's monograph. It turns out that those two domains coincide up to the value m equal to 3/2, and then the Dirichlet space is always smaller than the Navier space. There is a very delicate situation when m is equal to 3/2. But always the Dirichlet space is smaller, not at least not larger than the Navier space. The reason is that the two Laplacians naturally they born together with some natural boundary conditions that naturally are imposed on the functions in their domains of the two quadratic forms. So here I wrote two very famous examples, S, m equal 1 and m equal 2. But, okay. In any case, don't forget that the Dirichlet space is always the smallest in some sense. So once we have this, we try to understand which are the relations. We try to compare the Navier, the Dirichlet norm on the smaller domain that is this H tilde. The first result one can check by a couple of very easy computations is that whenever m is an integer number, then those two norms coincide. Because take, for instance, m equal 1, then this and this coincides with the very familiar gradient of u squared. And in general, they coincide for every integer m. But they are essentially different when m is not an integer number. And to see immediately that they indeed are different norms, one can make the simple computation. Those two norms are different because they give different answers under the action of the non-compact group of dilation. For instance, they are different for this reason. For instance, take, assume, to simplify, that 0 is in the interior domain of omega. Take any C infinity supported function with compact support in omega and shrink its support. Notice that when n is greater than 2m, that is when you have Sobolev inequalities, then it means this operation here means that you are concentrating the function u about the origin. Then you compute the Dirichlet norm of the UH, you find always the same result. It's an easy computation. But if m is not an integer number, then the integrals you obtain are different. Why? Because the Navier norm is defined through eigenvectors, eigenvalues of some problem on a fixed domain. While here you are shrinking in some sense the domains of the UH. Okay. And so indeed the two, when m is not an integer number, the two norms are really different because it depends on where m is. If m is between 0 and 1, or if the integer part of m is an even number, then the Navier norm is always greater than the Dirichlet norm. While when m is between an odd and integer number, the inequality reverse. Actually, in the abstract of this talk, I promised only the case m between 0 and 1. But this is the complete result. The case m between 0 and 1, we studied that case in this paper that has been already published in Communications in Partial Differential Equations, while in this preprint archive, August 2014, we have the complete result for every positive order m. So this is the complete result. Let me very quickly show the outline of the proof. The first fundamental step is the result, indeed, is one of the results that is contained in our paper in Communications in PD. And it's to take the result in the theorem when m is between 0 and 1. This is indeed one of the most largely studied cases, m between 0 and 1. Okay, and our argument is based on this very now popular, famous, celebrated, very useful, powerful technique due to Caffarelli's investor. The idea is to look at u, so you have fixed u in the Dirichlet domain. In this case, they are the same. In the Dirichlet domain, you fix a non-trivial u there. And then you look at u as the restriction of a function w of n plus 1 variables on the boundary of a half space. So w is defined on an n plus 1 dimensional half space. And then there is this Caffarelli-Silvestri technique that has been generalized in much more general situations by Stinger theory a few years later. The argument is the following: define this energy, this is a weighted Dirichlet integral, and define this energy on the class of maps that have on the half space that have finite energy and whose trace is given by the fixed function u. So you can consider this energy on the space. It turns out that this energy is bounded by from below and coercive from the space and blah blah. But you can also consider the energy restricted to this smaller set. In the smaller set red, you impose also some Dirichlet, homogeneous Dirichlet boundary conditions on the lateral surfaces of the cylinder. This is Rn plus 1, and this is Rn, more or less. Yellow means W is equal to 0 there. Not a nice draw, but it doesn't matter. So one of the main results of Caffarelli-Silvestri and then of Singatoria is that the blue infimum gives the Dirichlet normal view, and the red infimum gives the Navier normal view up to a constant Cm, which is the same and which depends only on the dimension and on n. And now, of course, there is a very simple argument that starts this constraint in red is smaller than this constraint. This means that the red infimum is larger than the blue infimum. That gives you a large inequality, but in the right direction that is predicted in the theorem. Now, to conclude that indeed, if U is non-trivial, then the strict inequality holds here. The argument is simple. You argue by contradiction. You assume that they are equal, so there is a function W that achieves both the infimum. Since W achieves, say, this infimum, then W solves some equation on a half space. Since W achieves this, then W vanish on a large set. This means that W, since it has to be analytic, this means that W is 0, that is, U is 0. If U is not 0, then necessarily the strict inequality holds here. That's fine. And the second step is an easy step indeed, because you have to handle the case when M is between an even and an odd number. And you simply use some associative properties, and you simply use the fact that for integer order, the Navier Laplacian is a reiteration of the standard Laplacian. So since we know the situation here, we know which is the right inequality, say between 2, 3, between 4, 5, and etc., etc. That's really an easy step. Of course, here we use step 1, the case M between 0 and 1. The third step is more difficult for sure, as the step between 1 and 2. Of course, if we understand this, then we understand also the step, the region between 3 and 4, 5 and 6, and so on. So this is a crucial point. How to handle this area? Here the answer is, if you want to understand what does it happen here, you have to understand what happens here. So you have to understand which is the relations between the Navier-Dirichlet norm for of negative orders. So actually at the beginning of this seminar I started to introduce the Dirichlet, the Navier Laplace, fractional Laplacians of positive orders. But by following this more or less the same outline, one can also talk about fractional Laplacians of negative order. The definitions are not very different, indeed. And so we have Navier-Dirichlet norm also here. We have the Dirichlet space also here, which turns out to be smaller than the Navier space. So we have to understand what happens here to the norms, fractional negative norms of fractional and negative order. And to understand what happens here, according to the statement of the theorem, we have to prove that here the Dirichlet norm is greater than the Navier one. If we prove this, then an argument similar to the argument in the previous slides gives you immediately the full result. That is this. This is the statement of the theorem I showed you. Well, I will be very quick here. To handle the case of fractional negative Laplacians, we propose a dual extension argument. It's dual, of course, because it's in some sense dual with respect to the Caffarelli-Silvestre and the Stinga-Torrea extension argument. We introduce a dual energy and so on. So M is between -1 and 0. This is the last step we have to deal. We take U in the domain of the Dirichlet norm. Now, it turns out that the Dirichlet norm, the Dirichlet space, the space is a subspace of this one. So any U here, say non-trivial, is indeed a continuous linear form on the Sobolev space H minus M of Rn. Minus M now is positive. Hence, we define this functional. Well, W now is not an extension of U at all, because this is a dual. This is not a direct Caffarelli-Silvestre argument. W is a function on the n+1 dimensional space with no boundary conditions, but we let W run in this space. What is this? This is the duality product between this space and H minus M over N. Also, as before, we have a smaller space. Here we prescribe Dirichlet boundary conditions on this lateral surface of the cylinder. And we prove a dual Caffarelli-Silvestre Stinga-Torrea result. Actually, the proof is not so long because this is indeed a corollary of the Caffarelli-Silvestre and Stinga-Torrea lemma. Okay? But now, please pay attention. Here we have some minus sign due to the fact that we are working in a dual way. And because of this very important minus sign, we obtain the reverse inequality with respect to the positive case. Because again, the red set is small, is contained in the blue set. That is, the red infimum is larger than the blue infimum, but due to the minus sign, then here we get the opposite inequality. The energies in this case infimum are negative in this case. And then, of course, to get the strict inequality here, you argue more or less as for the positive case, and you conclude. Oh, I should also say that this argument goes almost finally when n is greater or equal than 2. When n is equal to 1, one has to pay some attention in some points, but everything goes well. I think I always prefer to stop 2 minutes before than 2 minutes later. So I just mentioned the fact that we also have distributional, inequalities in the distributional sense for non-negative functions. where U is non-trivial, we already know that the Navier norm of U in this region is strictly greater than the Dirichlet norm. Actually, we also have for non-negative U an inequality in the distributional sense between those distributions. Those are differential operators. There are some, of course, always we use the Caffarelli-Silvestri and Stringa-Torrea lemmas. That is the base of all our results in some sense, but we also use a very refined boundary point lemma that is a recent result by Alvarado, Brigham, Mazia, Vitré, and Gedet. And please let me conclude to go back to the first remark I made about the role of non-compact group of dilations. I already observed that for non-integer m, the answer of those two norms with respect to dilations is different, but the last result I want to show you is that at the end of the story, the two norms are not so different because in the limit, the Navier norm always in the limit, always realizes the Dirichlet norm that's called for any m greater than -1, something like this. I think I can stop here. I hope you have heard me, and thank you very much for your attention.
Are there any questions or comments?
Tell me this. You mentioned non-local operators corresponding to long-distance interactions. What kind of non-local operators do you consider? I didn't understand.
Oh, non-local operator?
Non-local operator.
Operators.
Operators, non-local. What does it mean, non-local?
It means, for instance, the Laplacian, the Dirichlet Laplacian is a no-local local operator is the Laplacian because it's the trace of the Hessian matrix that is made by derivatives, and the derivatives are pointwise defined. While here you have, in some sense, a generalization of derivatives, but it's something that you define through integration on the space. So that I don't. For instance, we are looking for this is. I hope this is psi 2m the Fourier transform of U.
In the left-hand side,
too many f and half. M squared over 4 is.
So you need fractional powers.
Yeah, in case, okay, of course, in case of when m is an integer, then you recover the Laplacian, and when m is an integer, then this is always some. This also is a notation often used.
Thank you, I understand.
In that sense.
Continue with the question here.
Yes,
Because
please.
when you have an integral, a non-local interaction, which you have integral operator, which space do you take for your definition?
Pardon, I cannot hear.
If you have this integral operator, now you have two different kinds of definitions which are also blended, which they differ. What do you choose then? Because we have to show that the integral operator can be described.
No, I just want to say that I mean I think there are incredibly large class of operators that, for instance, physicists use, and also in new materials I saw something and so on. This is the reason why mathematicians cannot understand physics. mathematicians started to study those operators deeply, in particular those two operators. I just said this one. And in particular, I mean, those are very well-known operators, but in the last year, they have been studying, it's a trendy argument, let me say.
No, I just want to comment. If you have this application, you have to find out which kind of definitions you have to take to approximate.
That's not my thing.
This is
but I can say pay attention, they are not the same.
Yeah, it's really difficult if you look at the so-called diffusion processes through
That's not my intention. That's not my intention. But the applications encouraged a large effort in studying those operators and understanding those operators from the mathematical point of view. This is.
Yes, Professor Veron, please.
On the last
Yes.
page that you show, I think when you go to the last page of the revision, it says there is a difference.
This is.
No. The one where you have the integral of radium m square is bigger than this one. Okay, no, well, this one, I'm sorry. The result of Nazarov U in research matter is this integral of the fractional Laplacian m over 2, the local one, to the square is strictly bigger than the other one for positive function. Can you go back to this form? I think it was in the last.
Yeah, it depends on where m.
Last slide, probably. The last was the last one.
The last.
Yeah, this one. Yes. Okay. Now, what is the you have this expression, and do you know something about the difference between the two forms? What is the difference? What is exactly if you make the difference between?
Oh, that's an I mean.
Design of u minus the other one. What it is? It is.
But this just means that you. I mean, are you talking about? Are you asking about an open problem, or are you asking about the definition?
Do you know something about what is?
No, this is really. Thank you. Really, I think that also for the norms, one can understand.
Yes, for the norm, for example, does it is something like?
I mean, let us fix the m between 0 and 1. I would like to find something to put below the difference Navier minus Dirichlet. That's an open problem as far as I know, and I thank you for your question.
Any more questions, comments? Then let's thank the speaker again.
No. I lose the collaborators.
Because it does the sign of u. It does the sign of u.
No, I mean in the distribution of well,
in the norms, okay. In the norms, it looks like the story of hard inequality. Improved hard inequality.
Professor Musina, excuse me, please. So you are the chair
Yes.
after the break. So this lecture is cancelled. So is it possible to move this lecture?
No, because they already arranged in a different way. That is Juan Davila
Yes.
will give his lecture because he was at the same time as Ignacio Guerra. And many people could be interested in both of them. And so Professor Veron suggested to insert Juan Davila here.
Поздно переносить?
Да, поздно уже назначили этого Хуана Давилу на эту лекцию.
А, назначили?
Да, да, да. Потому что многие хотели его послушать, и этого. И Хуана Давилу, и Игнасио Гуэру, двух чилийцев.
Да, будем сейчас говорить, сейчас чужие. Говорим сейчас вот это.
Просто вы как что-то предложили? Okay, so the last talk before the coffee break is by Professor Ilyasov, Pokhozhaev's identity and compact supported solutions.
Thank you very much for this. Yes, for this possibility to give the talk. My talk is dedicated to the memory of the Pokhozhaev. I begin my collaboration with the Pokhozhaev in 91, 92, and also I have the joint paper with the Pokhozhaev, but he was my supervisor and also was my friend, and this was a real collaboration because we discussed a lot of problems. And I choose my talk about the Pokhozhaev identity because we get something new concerning this identity, and the main subject is of my talk to introduce that the history of this identity is not finished, and we can find something new. So, but I begin from the classical result. So, if we consider this kind of problem, then we can prove this identity. It's not difficult to prove. Simply tested this equation by the ux multiply x, integrate to part by part, and we can get this inequality, this identity. And this identity was obtained in 1965. And I suppose that this is the main famous result of Pokhozhaev. In Google, this show that cited by this number of authors. I little bit maybe told about the history of this identity, as I know. When he got this identity, of course, he didn't know that this is would be famous identity, I suppose so. And the first talk one of the first talk he gave in the seminar of Kudryavtsev, and Kudryavtsev is known that this is maybe very interesting result, non-existence. And the name to this identity was given by Nirenberg when he one time visited Moscow to the, I think, to the Petrovsky conference. This is famous, our conference in Moscow State University. And when he told his lecture, he said that now we will use this identity, and this identity was proved by Russian mathematician Pokhozhaev, and people said Pokhozhaev is here, and Pokhozhaev stand up. He was young, and he said now it will be Pokhozhaev identity. And after this is Pokhozhaev identity become. So what is important from this Pokhozhaev identity? So a little bit, I repeat. If we consider G like this, then we have this we call Nihari manifolds identity. Simply if we test the equation by the U, and we have Pokhozhaev identity. From these two equations we get this, and simply we multiply this equation by 2n over n minus 2 and subtract it from this, and we get this. And we see that all this term is positive if this term is positive. So if Q is greater or equal to star, and omega is star-shaped, that's so this term has to be positive, then all these terms positive, and this problem has no solution except 0. So in these cases we have critical exponent,
And, and we can call this, this number Pokhazaev critical exponent. I will explain why later. Because usually this exponent appear in as the Sobolev critical exponent. And so the points, we have this embedding theorem that this means that here is embedding and this compact embedding if the Q is less than the P star. P star, this now instead of 2 we put P. So, so it turned off that this critical exponent from the embedding theorem coincide with this simply from the, this is if we consider 2 this equation, we obtain the same. So actually this is still open problem. Why these 2 constants coincide? This naturally is, there are not natural explanation why it happens, because this is simply from the sum, if we consider function 1 over x in power alpha and put that this belongs to this, and this term appear. But why it happens that we simply made some trick with the Pokhazaev identity and the Nihari identity, we obtain the same. So let me begin with another cases of the critical exponent that was discovered recently, that also appear from due to the applying Pokhazaev identity. So let us consider this model problem. So this is directly problem, but we add this condition. So if this is overdeterminant problem, and so if we get solution with this condition, we call this compact one. Sometimes it's called compact support solution, and sometimes it's called the free boundary solution. So what is known about this? If these conditions satisfy, we say that this is the solution satisfy Hopf boundary maximum principle. So if beta less than the alpha, then this term when u is small become positive, and of course we will have this Hopf boundary maximum principle, because this right side is the positive, non-negative. And next we have this result. If this both term of greater than 1, then the right side is the Lipschitz functional, and also we have this Hopf boundary maximal principle is satisfied. But just a moment. Yes. So let's consider these cases when alpha is less and beta less than or equal 1. And so in these cases we have like this theorem. There exists some lambda star, so that for any lambda greater than lambda star, this problem has a compacton. So this was proven in 1990, and then some generalization for the P Laplacian. And this result was obtained with Yegorov. I will mainly speak about this result here. And these cases when beta greater than 1 was obtained by Cortázar, Algueta, and Felmer. And this also, they prove that any compact solution is actually a radial solution. And now I explain how can we use another technique that was introduced by Pokhazaev. This is fibering analysis. He introduced in 1979. So let's consider again Pokhazaev identity for this equation that we consider now. Then, under assumption that omega is star-shaped domain with respect to 0, we have, so this term has to be 0. And so right side here has to be 0. And we has to have this. I call this as Pakhajaev functional. So if we have a compact tone, this term 0, and we have to have this equality, this functional of Pakhajaev is equal 0. I know that the problem is in variational form, so any solution of this problem has to satisfy to this equality. This is again the Nihari identity I call. So this can be obtained if we put here T, this is technique fibering, differentiated with respect T and put T equal 1. But it's not convenient every time to think about T equal 1. We put only like this. So if we have some solution, it has to be satisfy this for some T. And as I told that for the compact supposed solution has to be satisfy this equality. So if we want to find the compact supposed solution, we have to have these two equality. So one of idea to obtain compact support solution is the following: to minimize this over this constraint. And how it's work? So if we get the solution of this minimizing problem, then we, by the Lagrange multiplier rule, we have this. And it can be proved that there is some lambda star that says that this multiplier is equal 0. In this case, we get from this equation, we get that U is solution of our problem, but by the constraints we have this. And this means that this is compact tone. This is idea how to use Pakhajaev identity to obtain compact support solution. So this is Pakhajaev identity work not for the proving non-existence, but for the proving existence of solution. But this is not the main subject. Subject, the following. I call this spectral analysis with respect to fibering. So consider this again problem. I told that this is because beta less than the alpha. This is the case of when the classical Hopf boundary maximal principle satisfy. But I explain how it can be obtained by the fibering. So let's consider fiber functional. So we simply take our energy functional and put here T. Then we obtain these functional, and we fix U and draw the picture with respect T. And we see that since the beta less than the alpha and beta less 1, first beta is the main term near the 0. Due to this term, we go to the down, and then both of these terms take this our functional in this direction. So for this equation with this condition, if we have a solution, the solution has to correspond to the minimum of the fiber functional. Let us now draw the picture of the Pakhajaev functional. It's easy to see that Pakhajaev functional can be obtained like this. So Pakhajaev function has to be a little bit less than this functional energy. So we know that a solution has to be like here. But since this, we see that P never will equal 0 in these points. So if we want to obtain the compact support solution, this has to be coincide with this. But in this case, it never happens this. Simply we draw this picture how it's work fibering methods. Only by this very quickly we can analyze by the fiber techniques. So let's us consider more difficult situation. So this situation when alpha less than the beta and beta less than the 1. So we again draw the picture, this. But in this case, it's because alpha less than the beta. First work alpha, we go like T in power alpha plus 1. Then this term play game, and then this term. So we have two maybe two solutions, because this we have maximum and minimum. And Pakhajaev functional is below of this function. So if we want to find compact tone, we try to find the cases when these points coincide with these or these, and these with these or these. So idea is only analyzed when these coincide. So arise the question, is it possible that this will be coincide? And the answer is the following. So I call this spectral analysis. You remember when I begin my talk, we consider when classical cases. Sorry, we study this system of equation, and sorry, I think not. It's impossible. Sorry. It was not a good idea to return. So this idea is the following. We want to get, if we want to get the solution, we have to, it has to satisfy this. I put t now equal 1. And we have to have the Pakhajaev identity equals 0. And we study this also at the cases, because this is boundary cases. I told that in one point we have the second derivative with respect to t, it has to be non-negative, this non-positive. So we study this system of equation, and we study with respect this term gradient, this and this, and consider like this linear system of equation. This we have coefficient 1, and minus 2 over 2, 1, this 1, and so on. If we consider this matrix with this term, then if this problem is solvable, if this determinant is equal 0. So this can be solved, and we find this something. And this is new critical points. This is critical dimension. Let me explain in which, in the sense of this. So, what we have, if n less than this, then if we have compact tone, this has to be, the second derivative has to be negative. In these cases, it has to be positive, and in these cases, it has to be equal 0. So we have several 4 different cases. So if we have a compact tone, in these cases, compact tone correspond only to the maximum of the energy functional. In the second case, compact tone here, it can be coincide only with these points, with the minimum of the energy functional. In the case of the n equal n star, this is case when these 2 points coincide with. And different case is n this n has to be capital. This case is because in the Pakhajaev identity, this term, when n less than 2, this become negative. So this is 4th cases is little bit different. This Pakhajaev identity function like this. So now let me explain why it's, what it means critical exponent. Critically means the following. This is recent result. So if n greater than n star, then if we consider this problem, the compact support solution is stable, because we work with these cases. We work with this compact solution that correspond to this case of energy functional. But if the n less this, we can expect that this solution will be not stable. So this is proven. So in this sense, this dimension n star is critical. Of course, we can fix n and study this problem corresponding with respect to alpha or beta, and will appear some another kinds of critical exponent with respect this exponent, alpha or beta. In this case, more beautiful if we take this simply. So I want to explain another cases also when we use again Pakhajaev identity. Let's we consider this problem with P Laplace, and this is double well potential. So this functional has two minimum and one maximum, and this in case alpha equal 2, this is Cahn-Hillard equation. And we consider the problem when omega, in omega 1 streaks. So this is some omega 1, and here this big omega, and in this area we study the problem. And the phase transition solution is like solution like this. First solution stay in the one stationary points of our problem, then they mix from the one phase to the another. So the question is if that such kinds of solution exist. And this solution is called phase transition. What is interesting, in case equal n equal 1, this is studied, it depends from the p and also from alpha. Sometimes this is also put beta. Yes, like this. So it was proven by Drabek, Manasevich, Takac, and also Rosenau, Kazdan, because it's physically interesting cases. So they prove that this problem has a phase transition solution. But at the same time, if we consider these cases, then has no phase transition solution. I forgot this, if alpha put equal 2. So the question is, what will happen if n greater than 1? And answer is very simple if we use, again, Pakhajaev identity. If we write this Pakhajaev identity, we will get this. And not that this is by integration by part, we get this. And because this term by the assumption u is equal 1 or minus 1 on this boundary, so this term has to be 0, and we get the following. And this also has to be 0 because by the assumption we suppose that solution is phase transition solution. So we get this identity, but this is impossible. This is possible only if w equal 0, but this is possible only if u identically equal 1. But we in our assumption we put that in one boundary is equal 1 and the second boundary is equal minus 1, for example. So this is one of the results how to can be used Pakhajaev identity to study like this problem. So I am also what I note. What the part in this result? This is result with Professor Takac. This is problem with the P Laplace. We have no solution classical. We cannot prove that this is a classical solution. So it's necessary to prove Pakhajaev identity for the weak solution. And what is the new in this paper? This is, it can be said that this is one of the, this is proof is new because something was invented in this for the proving in the weak sense. It should be noted in some papers there is gaps when they try to prove this for the big solution. So this is some papers concerning this investigation about this my talk. So I am finished. Thank you very much.
Thank you. Are there any questions or comments? Please.
This is your last equation. Was equation of second order was also you call it computer is maybe Allen Kant second order equation.
No, this is sometimes this if depends from the this if in alpha.
Second order equation is Allen Kant, not computer. Computer is equation of fourth order.
Oh, I don't know. I took from the maybe I. Yes, Alan Kant. Yes, maybe yes. I made mistake. Yes, thank you.
Some more questions, comments? Yes, please.
I'm very much interested in your results with compact support.
Yes.
It reminds me a little bit with the problem what is the Cauchy, what in the linear case what I would consider Cauchy problem at infinity. You need this Cauchy problem at infinity, not to take into account what happens in finite parts, but in the infinite part.
Yes.
There one uses inequalities or these weighted norms.
Yes.
Yes,
yes. We now we prepare. It's very. I do not speak about this as weighted function, but if you we now prepare some paper together with. Yes, yes. You know, this is there is the book Shubin-Gelfand, and they prove they call this is Kato lemma, and they use this is very important for the Schrödinger equation. Yes.
I did my PhD on that and generalized that.
Yes, wonderful, wonderful.
And there's an open problem which I think is good conditions on an elliptic operator on the higher order and asymptotic behavior which guarantees if the right-hand side of the equation says compact support,
Yes.
the solution must have compact.
Yes, yes, yes. I know.
It's an open problem.
Yes. Thank you.
I asked Hermander what he can do.
Yes.
He said it's too difficult.
We can speak later because I thought about this also. I read when I work with this. I study this, so it means that this is your work. I studied from this, but in the books of Gelfand and Shubin, they don't call this as Pokhazaev identity. I don't know. Because I think it's sometimes it's also called the virtual identities, something like this. Okay, thank you for the question. Yes, very interesting question.
Okay. Any more questions or comments? Okay, then let's thank all the speakers again.
Thank you.
And now the coffee break starts.
No, no, it is.
Sorry. No,
Cigar.
cigar.
Cigar. When you finish your picture, then we can start. Whenever you have finished it. So I think we can start. I will use the microphone. It's really a pleasure for me to open this second part of the session dedicated to Professor Pojaev. You can see a picture here of picture of some years ago of Professor Pojaev with his great friend Enzo Mitidieri. So please take your. Now the first speaker now is Professor Galatkov. He will talk about non-existence of monotone positive solutions to a quasi-linear elliptic inequality in a half space. Thank you.
Thank you for your introduction. Yes. It's a joint talk with Olga Saliva, and the title was announced. We would also like to thank the organizers for the opportunity to take part in this conference, and in particular in this session dedicated to Professor Pohojaev. Yes, we would like to start from the original problem. You can see problem 1 here. And the question is, for which values of the parameter Q non-trivial solutions of this problem do not exist? It's a problem in a half space, Rn plus. This problem in some special cases was studied by the authors mentioned here. Namely for the case of where A equals the gradient of U, so the operator in problem 1 is Laplacian. And the range, they obtained for Q is like this.
It is the range with non-existence.
Yes. Then there were some generalizations, but the most interesting problem for us is the one where A has this form, so the divergence of A is the P Laplacian, and it was established by Bidoveron and Pohojaev that there exists a positive constant such that the range of non-existence looks like this, formula 2. Further, our question will be, what is the value of this constant gamma Pn. The method of study used by these and other authors is the method of nonlinear capacity developed, developed by Pokhozaev and Mitidieri, and based on choice of a family of test functions depending on a parameter which characterizes the size of the support of these functions. And you obtained some a priori estimates and then took the parameter to infinity. The difficulty consists in the case of a half space, unlike the whole space, consists in the fact that as you see on this picture, so that's xn, and these are other variables. And so they had to use test functions like this, with 1 here and equal to 1 here and to 0 in such a rectangle, and 0 outside of a larger rectangle. And the problem is that, unlike the whole space, it is impossible to extend this support beyond the boundary. And there appear boundary terms which are difficult to estimate. So what is the way out of this difficulty taken by us? First, we changed the test functions by shifting their supports from the boundary, like this. So that was the first part. And the second part is related to the first one. So we restricted the class of solutions under considerations to the ones that are monotone non-decreasing with respect to the variable xn. So if we can estimate the test functions far away from the boundary, then due to monotonicity, these estimates can be extended to the neighborhood of the boundary. This can seem an artificial restriction, but the justification of this way follows from results of Farina, Montoro, and Sciunzi, who considered a special case of this problem. Dirichlet problem for the respective equation, and they showed that all weak solutions of this problem, which are essentially bounded for p between 1 and 3 and q greater than p minus 1, are in fact monotone, non-decreasing with respect to xn. So using this way out, we obtained the following main result. So under these assumptions on P and Q. The problem 5, which is a special case of problem 1 with the P Laplacian, has no non-trivial weak solutions in C1 local that are monotone non-decreasing with respect to xn. So this result corresponds, gives an answer to the question we put in the beginning. What is this gamma Pn? So it has this form. So the scheme of the proof is based on the choice of non-negative test functions, which are whose supports are shown on this picture, where lambda is the positive power, a fixed positive power. Rho is the parameter characterizing the size of the support, and the function xi rho, t sub rho, can be represented as a product of functions with respect to xk, and the function with respect to xn is shifted by 3 rho upwards. And then after some transformations and using monotonicity of U, we obtain estimate 8 of some positive function of the solution, where we have on the right hand side 2 terms, I1 and I2, that depend on the parameter rho. Here we choose lambda large enough so that integral converges. And the parameter alpha can be chosen small enough. And in this case, the first integral on the right-hand side of 8 can be estimated like this. And as rho goes to infinity, this term tends to 0. That's for any p larger than 1. And the second integral in 8 is estimated in different ways for the cases of p less than 2, the singular case, and greater than 2, the degenerate case. The case p equal to 2 is already known. So for p between 1 and 2, we subdivide the integration domain into 2 parts, where some quantity is small and where it is large. Where it is small, well, the part where it is small can be easily estimated, and where it is large, we estimate its negative power and integrate the rest by parts. And then after some transformations, we obtain the claim for p between 1 and 2. In case p greater than 2, is even more simple. Here we use just the Young inequality with appropriate parameters and also monotonicity. And the proof is completed similarly to the previous case. There are some possible generalizations of these results for operators with variable coefficients dependent on u and x, and for quasi-linear elliptic systems. Oh, and here there are some references. So that's all. Thank you for your attention.
So we have time for where is the
Yes.
In our paper with Rochaev, this coefficient gamma Pn was not known, completely known. It was on the form of P over beta and some beta,
Yes.
which is unknown except when P equals when
Yes.
n equals 2. Did we try to compare your coefficient with our coefficient when n equals 2?
Well, it's not yet, but we will. But it's an interesting question. We will try to compare these coefficients.
Do you have existence for great exponents? You formulated as purely non-exponential.
Well, there were some. As far as I know, there are some existing theorems for the Laplacian, but for the P Laplacian, not here. Yes. So it's a purely non-existence result.
Yeah, formally speaking, it is not yet complete.
No, not yet. Not yet. Maybe that's not the optimal exponent.
I see.
So that would give you an estimate from above also.
Yes.
On
Yes,
that,
just estimate from below.
Are there any more questions? If not, we thank again the speaker. We have 5 minutes break. We are in time, but we have 5 minutes break. Since this problem is in a half space, I will not. Okay. Here it's similar results. Here with distance from some glasses here. Are yours? So you can also say, tell me the right pronunciation of your name, surname.
Tsaggo.
Huh?
Tsaggo.
Tsaggo.
I'm just the final one.
Yeah, I can
I
see. I can understand. Waiting for.
Just installing it.
But can you read the Russian?
Yes, installing it.
Fantastic. Help yourself. So we can start again with our second speaker. Let us start again with Professor Juan Davila from University of Chile, Santiago del Chile. He will talk about fractional minimal surfaces.
Okay. So I want to thank the organizers for the invitation to the conference. This is joint work with Manuel Del Pino and Yuncheng Wei. So let me define a fractional mean curvature. So I will let's say you have a smooth hypersurface in Rn. I first recall the standard mean curvature, which is the sum of the principal curvatures. Yes? Sorry. So, and then the fractional mean curvature is this expression over there. You take a number s between 0 and 1 and compute an integral over the surface. That it is, in some sense, a fractional divergence of the normal vector of the surface. So let me motivate this expression here, mentioning one instance, one example where this appears. So for this, I want to first describe a discretization for motion by classical mean curvature. So this discretization was proposed as a numerical scheme to compute or to approximate a motion by mean curvature, and is well, it was done by or proposed by Berryman, Bench, and Osher. So you consider an initial set omega 0, let's say open bounded also if you want, boundary I would call sigma 0, and let tau be a discretization parameter. Then you solve the heat equation, over here with initial condition equal to 1 inside the set and minus 1 outside the set. And let that heat equation evolve, and you are interested in the solution at value tau, at time equal to tau. And then you look at the level set u equals 0, or let's say u positive, but at time tau. And this defines a new set. And with that new set, you repeat the procedure. And so if you let tau k be the sequence of numbers like this, tau to tau, etc., omega k be the sequence of sets like this, and consider that tau goes to 0, this scheme converges to a mean curvature flow, and this was well suggested by them and proved rigorously by Evans. Okay, and then Caffarelli-Souganidis proposed to study what happens if you consider here the instead of the heat equation, the heat equation associated to the fractional Laplacian. So the fractional Laplacian for a, let's say, a nice function u in Rn is this expression over here. Motivation to study this type of numerical schemes comes from a field called threshold dynamics, where somehow you choose a law of motion. In this case, this is the, let's say, one of the simplest kernels you would think after the case of the Laplacian. More general cases were studied here. Okay, and then you run the same schema as before, but let's say we discretize time by a step delta, and then now you have, sorry, we discretize time with the time with a step delta, but we stop the heat equation or the fractional heat equation at time tau. Okay. And then it was proved by Caffarelli and Souganidis that if the sigma, the power going into the fractional Laplacian is greater or equal than 1/2, and you choose tau correctly, depending on the parameters, then this scheme still converges to motion by mean curvature. While if sigma is less than 1/2, and again you have to make the correct choice of the tau, then the scheme converges to motion by fractional mean curvature with the expression I mentioned at the beginning. So other motivations to study these fractional minimal surfaces come from some version of phase transitions where you measure interaction between particles using, again, a fractional operator. And this is done in many papers, but these are, let's say, early ones about dislocation dynamics and phase transition with line tension effect. Okay, so the fractional mean curvature is this expression here. If the surface is the boundary of a smooth set, E, then integrating by parts, you find this other expression over here, which is a principal value integral, well, the expression over here. And we're interested in fractional minima surfaces. These are surfaces for which this quantity is 0. Okay. So there is a notion of fractional perimeter that, sorry, yeah. That was introduced by Caffarelli, Rocajoffre, and Sabin, and is the following. You take a set E and formally consider the double integral over here with the singular weight. This is nothing else than actually, well, 1/2 the semi-norm of the characteristic set of E in the space WS1. Okay? There are other expressions, but this one already makes sense or was studied somehow before. So in principle, this can be infinite, because if the set has, let's say, infinite boundary or unbounded boundary or very rough boundary, this could be infinite. But let's say we take this formally and we'll localize it to a bounded set omega, but somehow discarding terms in the integral which will not enter in a comparison. So the correct formula turns out to be this one, is somehow a piece of the integral here. And then we say that a set E is minimizer of the fractional perimeter inside the set omega if this expression is less or equal than the expression for any competitor which is equal to E outside of omega. These are minimizers of this fractional perimeter. And the nice feature of this is that the Euler-Lagrange equation associated to this minimization problem is exactly a fractional perimeter equal to 0, at least for everything for smooth sets. Okay. There are some well-known asymptotics when S converges to 1. This fractional perimeter multiplied by 1 minus S approaches the classical perimeter when S goes to 1. And this can be seen from the derivation of this through the discretization procedure. Also, well, it was proved by Imbert. And in the case of the perimeter, this was already studied by Bourgain, Brecis, and Mironescu when they looked at what happens to the fractional Sobolev norm with S converging to 1. Okay, and so this was already known from before. But there was no, let's say, geometric interpretation. So Caffarelli, Rocajoffre, and Sabin, they proved that if you prescribe a set E0 outside of omega, and you minimize this fractional perimeter with the condition that outside of omega the set E is equal to E0, then this minimization procedure has a solution. And minimizers are regular except a closed n-2 dimensional set. Okay? So existence and regularity of the minimization is proved here. One still can wonder if there are surfaces which are minimal in the sense that satisfy the equation equal to 0 without minimizing necessarily perimeter, and there are very few examples. Well, a plane is actually a minimizer, and this needs to be proved, but it was proved in the same paper of Caffarelli, Rocajoffre, and Sabin. This set here, which is called Simon's cone, is a fractional minimal surface. Because of the symmetries involved in this set, you can compute the integral and you get easily that is 0 for all points on the surface. And also, not noticed before, it was the case of the helicoid is also a fractional minimal surface because it has enough symmetry to make the integral equal to 0. So the questions are, well, you have this definition, it's natural, it appears, but there are very few examples of fractional minimal surfaces. And also, another question is, what is the optimal regularity for these objects? So, well, for the case of existence, what we proved with Manuel Del Pino and Yunchen Wei is the existence now of a surface which is somehow decatenoid, okay? And this is done in the case when S approaches 1. So it is a case in which we expect the surface to be close to a catenoid in some sense, and this is the asymptotic shape that we find. If we call epsilon equal to 1 minus S, going to 0, then on the range, let's say we think of an axially symmetric surface. Here is the variable r. So if you think of r up to a range of 1 over square root of epsilon, the surface we construct looks like a catenoid. But from this point on, this looks like actually a cone. So this f is a function that grows linearly with a very small slope as epsilon goes to 0. We can also think of the following. If you think as S goes to 1, these surfaces should approach the classical minimal surfaces. Then a plane is a candidate, but also for the classical minimal surface, you have two parallel planes. It's also a minimal surface, if you want. And this is what happens to these two parallel planes if you let now S not be equal to 1, but very close to 1. And what happens is that on a large set, again of the size of 1 over square root of epsilon, this set basically is like a constant, but far away again grows linearly, and the behavior is that of a cone. Well, we can, in a similar way, construct surfaces with multiple layers, not only two, multiple layers here, and also more complicated surfaces, such as for example, you consider the Costa minimal surface, and then for S close to 1, there is a fractional minimal surface that is similar to this on a compact set, but far away, these ends that in the classical case grow logarithmically will grow like a linear function. And here you have an end that will behave like a plane at infinity, and again here you will see a cone. So about regularity of minimal surfaces, let me recall briefly the classical theory, so the theory for minimal surfaces. So in a series of papers by Fleming, De Giorgi, Algren, and Simons, it was proved that there are no non-trivial stable cones in Rn if n is less or equal than 7. A cone is a set which is invariant under scaling, okay? So it is written in this form, and you can think, well, what are the minimal cones? Yes, and you can find many minimal cones, and think about the stability of them. And the importance of this thing is that one of the consequences is that if you minimize area, then the minimizer will be smooth except a set of dimension n minus 8. Okay? This follows from the classical work of Fleming and Federer. Another consequence is that the Bernstein conjecture is true for n less or equal than 8. Okay? And so in the classical case, the study of the stability of minimal cones answers in particular what is the optimal regularity for, well, it doesn't answer nearly here, but what should be the optimal regularity for minimal surfaces. Actually, you can consider a general family of cones like this. Simon's cone, the one I mentioned before, is the case where you have R4, R4, and then here the equation is norm of z equal norm of y. And it was proved by Simons that this cone is stable. And Bombiri, De Giorgi, and Giusti, they proved that they are area minimizing. And therefore, this theorem here about the singular set is optimal. N minus 8 is the optimal dimension. Well, it is known actually in any dimension if the corresponding cones are area minimizing or not. So, well, this suggests, okay, what happens for the case of fractional minimal surfaces? It was proved by Caffarelli and Baldinocci that when S is close to 1, the minimizers are smooth except a set of dimension 8, which is expected because then the surfaces should be like classical minimal surfaces. But in general, the best result so far is by Savin and Baldinocci. They prove that cones that minimize fractional perimeter are trivial in 2 dimensions, and as a consequence that the singular set is at most n-3 dimensional. Okay? But then there is a gap between these 2 results, and then we decided to look, okay, what is the story at least for cones? And we consider a class of cones, so the analog of the loss of cones, but in the case of the fractional mean curvature. So these are still sets that can be described in this way for a parameter alpha that now depends on S. So we prove that for any dimensions n greater or equal than 1 and m greater or equal than 1, if you look for a set like this, there is a choice, and it's a unique choice of the alpha, depending on S, that makes this into a fractional minimal surface. And in the classical case, the cases n equal to 1 or m equal to 1 here are trivial. Somehow this corresponds just to a plane. In the fractional case, when S is not equal to 1, these are non-trivial cones. Okay. So let me mention what is the stability. What does it mean, stability? A fractional minimal surface is going to be stable if the second variation of perimeter is non-negative. And how do we compute second variation of perimeter? We consider perturbations of the surface sigma by smooth functions in the normal direction. Okay? And then this is the perturbed surface, and if this second derivative is non-negative for any perturbation, we say that the surface is stable. Actually, we computed the formula for the second variation, which is, it takes an integral form. It is an integral over sigma of an operator of h times h, and the operator has this form. It looks like a fractional Laplacian, an integral over sigma of this expression over here, plus h times a certain weight. Okay, and so, and actually this operator, it turns out to be very important in all of the constructions. And so what do we find? We find that if the total dimension, this is small m plus small m, is less or equal than 6, then all these Lawson cones are unstable. But if the total dimension is 7, then for S very close to 0, we find stable cones. Okay? And so this leads naturally to conjecture that for n, well, first, that these cones are not only stable for n equal to 7, but are also minimizers for n equal to 7 and S close to 0. And that if you think about any value of S, what is the optimal regularity that one should be able to prove is a smoothness except a set of dimension n minus 7. Okay. Thank you for your attention.
Questions or comments? Actually, I have a curiosity, but more or less, sorry, I'm not really involved with this. What about the constant mean curvature, fractional constant mean curvature surfaces? For instance, just spheres.
Spheres have constant.
Are they unique? We are in Russia.
Probably they are not unique.
I mean, so there is some literature about this.
No, no. Actually, well, we are actually trying to find them. I mean, in the classical case, you have the what are called the onduloids. I mean, these are like cylinders, but with a periodic structure. And these are known in the classical case. And well, we suspect that they exist for, actually we proved it, but still it's work in progress, that they exist also in the fractional case. But we know much less about regularity and other properties.
Maybe you mean the analog of Alexandrov. This is what you meant?
Yeah. Is it true that a closed
I'm not sure if it is known.
If spheres, they
of a sphere. No, the
No,
sphere
no.
is Konstantin Kervachev, but I don't know.
I thought the first question was, are the
sphere
spheres, have the spheres fractional?
Probably it's not known.
No, I think it's not known.
Probably not.
Good question in Russian.
Yeah.
Could you say a few words how you prove instability and stability? This is classical.
More or less, no, this is not. Well, we computed the operator associated to stability, and then stability of the cone means whether this operator is positive, well, actually negative with this sign probably. And in the case of the cone, so here you have something like the fractional Laplacian, and here you have a weight that in the case of the cone is exactly a power. So this type of operator actually is a fractional Hardy operator in the case of the cone. And the stability is related to whether the constant that appears here, this is a constant over a power, is bigger or not than the best constant for that fractional Hardy operator.
Other questions? So let us thank again the speaker. And we have a couple of minute breaks.
Fractional Riemann tensor. Question.
There is fractional scalar curvature.
This is a part of it, I guess. Not yet. No. But there are different definitions. There are even some units with definitions.
Yes, for the scalar curvature, for example. Well, for the scalar curvature, people try to consider a conformal operator, which is fractional and looks like the fractal curvature.
Yes.
And that, in an abstract setting, there is a definition. But I do not know that someone gives you the unique way to define it.
I would maybe open these files, but I think I couldn't. This is a flash. I don't know what's doing.
You have to go to here. This is your disk?
This one, this.
No, but this is your disk.
Is this mine?
Probably. This is?
Yeah, copy this one, I think. So.
My talk.
Leave it whereas it is, no problem. Put it there. Okay, thank you. And close it.
Okay.
Thank you very much.
Control L.
Yes.
Okay, let us start again. The next speaker is Ignacio Guerra. His talk is solutions for a semilinear elliptic equation in dimension 2 with supercritical growth. Please.
Okay, well, thank you very much for the invitation. I'm going to talk about a similar elliptic equation in dimension 2 with supercritical growth. This is a joint work with Manuel Del Pino and Mónica Musso. And so the problem is well known. I think it's classical that in dimension 2, well, one can have this minus Laplacian u equals to lambda times u times e to the power u to the p. Okay, so we look for positive solutions with zero boundary condition, and this problem, what we are going to look is for p larger than 2. So it's well known that this problem is critical for p equals 2. There is a series of papers of Adimurti, Prashant, Atkinson, Pelletier, De Figueiredo, Ruff, Del Pino Musso, Struve, Druet, where they prove, well, first in a ball that this problem is critical in the sense that this is the criticality of the Sobolev exponent, and then there are work of Atkinson and Pelletier in the ball, and and Struve and Druet asymptotics of for lambda going to 0. Well, there are many articles on this critical problem, but the thing is, what happens if p is larger than strictly larger than 2? So it's actually a no known what happened in that case. So with Manuel, we think about this and then try to look for numerics and then try to find a result, and then we find, I will show later the result that we find. And then, as I said before, this is the some of the results. There is, if you have lambda 1, the first eigenvalue of the Laplacian, then between 0 and lambda 1, there exists a solution. And this was proved first by Adimurti and Atkinson and Pelletier in a ball, and then by Adimurti in 1990 in a bounded domain. And there is no solution for lambda larger than or equal than lambda 1. So if you look at here, if u is small, then this looks like 1, so it's like the eigenvalue problem. That's why we have this this existing and non-existent results. So numerically, what you see is the following. So here is lambda 1, and then for any lambda, then you have a solution. This is a ball, and this is here this axis is the maximum of the solution. The solution is positive, and then you have U0, the maximum of the solution. And this is what happens in for u equal or p equals 2, the power here in u. And this is as we saw before, the same behavior occurs for larger dimension, but for the Bressis and Nirenberg problem. So to prove this result, they used some kind of similar results of Bressis and Nirenberg. And in dimension larger than 2, we have this problem. So for lambda between 0 and lambda 1, which is the first eigenvalue of now in more dimensions, and we have a solution. And here I put n larger than 4, because in this case we have the solution in between 0 and lambda 1. Remember that that in the three-dimensional case we have a special value of lambda where you have the solution between this value and lambda 1. So you can see, one can think of the same picture here for this problem for n larger than 4. And we try numerically, and what we found is that, for example, for p equals 10, then the solution also comes from lambda 1, and then for larger values start to turn. So apparently this turn doesn't end here, so you can follow this bifurcation picture, and then there will be a a value of lambda where this you will have infinitely many solutions. Okay, so we try to study this problem, and if you look at, for example, the dynamical system associated to this, if you try to do like Joseph and Lundgren did, the dynamical system is very it's difficult to handle, and then what we could do, I will tell later, is that you can find solution, but for p equals 2 plus epsilon. So if you are close to 2, then we can find this this type of we can construct solution in that case. Okay? But in fact, this problem is open. So, I mean, nobody has proved that this is the bifurcation diagram for this, even for the ball. And another thing that I would like to remark is that if you look at this, the same equation, but for n larger than 2, the behavior is the same as p equals 1. Actually, it's the same as the like Liouville equation with here u, but in the whole range of p larger than 0, in fact, that you have that the solution, you find infinitely many solutions for certain value of lambda in dimension 3 and 9, from 3 and 9, and a finite number of solutions for n larger than 10. Okay, so it's a partial result of Dancer was he proved that this you have infinitely many solutions for in this case. So this is the picture in n equals 3, and this is the picture for n equal to 10. Okay, and so what is happening is that, as I said here, in the case n equals 2, we have this diagram, and for p larger than 2, then we have something like this. So this resembles the case of the for n larger than 2, then where we have this result of Joseph and Lunden, where for the critical exponent you have well, in this case 2 solutions, because this is in 0 this is equal to 1, so we have a lower solution, and there are 6 infinitely many solutions for p larger than the critical exponent, and this exponent pc, which is the Joseph and Lunden exponent. And in this case, I put this case because you can find an explicit value of this lambda tilde where you have infinitely many solutions, where this solution make the terms. And for p larger than the Joseph and Lunden exponent, then you have only one solution. Okay, so this is the exponent, which exists different from infinity from n larger than 10, and in this case, we have an explicit singular solution. So what is happening is that the in this case, that here we should have a singular solution for this for a special value of lambda, where all these solutions here are converging. Okay, so in fact we see here that so the p equals 2 is in fact like a critical case. Okay, so for p equals 2 we have this, and then for p larger than 2 we should have something like this. And and I put also this other problem, which is very supercritical. Is a problem where you have a explicit singular solution, an explicit lambda tilde. This was found by Hempel in the paper doing other things, but he put this example. And then how it so if you do it this numerically, you find that this in fact you have infinitely many terms around this lambda tilde. Okay, so what we actually prove is the following. We couldn't prove for any p, so we look for this p equals 2 plus epsilon, and numerically what you find is that if epsilon is small, then the solution goes to, or when you u0 goes to infinity, then goes to close to 0, and then make a turn. Okay, this is for this epsilon, and for the other epsilon, another epsilon is this. So if epsilon is very small, this will go up and then will turn in at some point. And so this is our result, that in here for general domains is if omega you have a non-degenerate critical point of the Robin function, I will which is here defined here of this problem. Then for any k we have these positive numbers, and the solution looks like this k bubble solution. Okay, and outside this C naught, the solution looks like this, so like a sum of these Green's functions. So maybe to make a picture. So the solution we construct are the following. If epsilon is small, then this go like this. So numerically, is this more difficult to get? That's why I put the other picture. And so if epsilon is small, this goes up, and then this will be closer to 0. And for any lambda, then the solution that we found here are these. Okay, this and this. So this will be like a mountain pass solution, and then the solution that we found are these. So this for k equals 1, k equals 2. Okay. So to see the how is the solution. For in the case equals 1, the solution, as I said, looks like this. So it's like a Green's function of this problem with lambda, and with something small, with this correction, and near the singularity or the maximum, it looks like this. So this scaling is that the one we have to use for this kind of problems. So also appears in the paper of Dancer, where he looked for more dimensions. So you have gamma that's going to infinity, and then you have to put this term here, and then omega mu, which are these solutions, which are the solution of the Liouville equation. And in this case, gamma is, has this form, and rho, this, the exact or the right scaling for rho in a space here should be given by in terms of gamma. And here what we find is that mu, to have a solution, mu has to be a square root of 8 divided by e. So the idea of the proof is the following. We use Lyapunov-Smith reduction. So we need an answer for the solution, and then we prove that this we have an answer, and then we make an equation for the rest, and we prove that this rest is small somehow. And then the right answer is this one. So if you do this scaling with gamma going to infinity and rho go to 0 with this form, then if you plug into the equation, then you get this this equation here. And if gamma goes to infinity, then in the limit should be like the Liouville equation, which we know that has infinitely many solutions for mu positive. And we have to, in fact, we well, that was the first part of the answer, but the real answer is this one. So we have to match also the boundary conditions. So we take a solution like this, with this solution of the Liouville equation, and we add this term to match the boundary conditions. So if you put this, we can rewrite it like this, and then this looks like the Green function outside the C. And so, but here we need this to we need to have this small near the singularity, the C. So we take the mu like this. So this is like doing like this is like 0 or near 0. Then mu finally can be put in this form, and then we have this m, a parameter to fit. Okay, so this will be our answer, and then what we need to find the solution is the right m here, this parameter, and we do this looking at the energy of the ansatz, and so the critical point of the energy are the solution of the problem, and the critical points of the energy of the answer should be close to the real problem or the the problem we want to solve. Then the critical point of this energy, because I don't have the time, much time, then well you plug this the answer in the energy, and then you find look for the critical points of the energy now in the parameter gamma, and the parameter gamma or doing this differentiation in gamma, then you get that this should be 0. So the parameter m should be have this form, and then the real solution will have the parameter m with the with the m close to this value. Okay, well, thank you very much for your attention.
Are there questions or remarks? Dr. Sis, because we are 2 minutes late. We have a 2 minutes break. Thank you again. So the next speaker is Sokol. Some non-existent results for an anisotropic elliptic and backward parabolic inequalities. Thank you.
Thank you for the introduction. The title of my talk is some non-existence result for some non-existence result for anisotropic elliptic and parabolic backward parabolic inequalities. Would show me maybe how to use the pointer. How to use maybe
So this
just
is for
the light.
the light. Somebody switched. Somebody switched it. Okay. It's fine. No, it's fine.
It's fine.
Yes.
Yes. Let me use. So the my talk is titled by some non-existence result for anisotropic elliptic and backward parabolic inequalities. In this talk, for n greater than or equal to 2, and for such a vector, we consider the elliptic inequalities with equation number 1 and a backward parabolic in problems with equation 2 with an isotropic operator is given, I think, in equation 1 to the right hand, to the left hand side of inequality. In this case, I think here we have to consider the parameters Li, alpha I, Mi. In the case of parabolic problem, I think here Ki, beta I, Ni, all these parameters are positive integers, and the lower order, that's Li and Ki greater than 1 for each n. In this case, I think to the right-hand side of the inequality, A0 and B0 are some positive constants. And we have to consider here the parameter Q and Pi. Q must be greater than for each Pi in this case. Now I like to mention some known results which is related to these inequalities and these problems. The first one, I think here about existence and non-existence of solutions of inequality 1 and problem 2. In the case of an in the case of isotropic one, that means when Pi is equal to 1 or Li is equal to, I think from the inequality here, Li and Mi are either equal or maybe Li is equal to fixed 1 in the case of this type. Or in the second line, I think Li may be L, all Li's are equal, or all Mi's are equal, all Ki's are equal. In this case, I think these known results are obtained by these authors. In 2001, Dmitry and Baujev, Galav, and so on, I think in this case. The second one, I think here, the question of existence and non-existence of solution to a backward parabolic case was formulated by Baujev, I think in this case. The third one, whereas in the case of an isotropic case, that is the questions of existence, uniqueness, as well as I think regularity of solutions for elliptic inequalities and parabolic problems with different anisotropic operators, but without operators, which is given in equation number, inequality number 1 and equation, I think, 2, or problem 2, were studied by, I think, these different authors. In this talk, I think the main objective of this talk is to prove non-existence theorems of non-trivial weak solutions to inequality 1 in the case of elliptic 1, and in the case of 2, I think the backward parabolic problems. So now let us go to the elliptic inequality case. I think here, see number one, I think in this case, the inequalities or anisotropic elliptic inequalities. So in this case, I think here to find the non-existence condition for such inequalities, first let us introduce the admissible spatial function of this solution. This solution, in this case, we have to define or we have to denote, I think, the admissible solutions in the form of, I think, here LP space of with vector P bar. We can denote, in this case, it is the intersection of all LPIs of local integral functions. For, in this case, I think Pi must be greater than or equal to 1. So we have to formulate, I think, the definition of weak solutions for these inequalities. As stated here, I think here we have to formulate the weak formulation. For any function u from LQ or locally Q intersection with the one functional space stated above is said to be, I think, a weak solution. So for any non-negative function, the so-called, I think it is test functions with compact support, this integral inequality must be held true. This integral inequality must be true. I think this one is the definition of, I think, what we mean by weak solution for these elliptic inequalities. Thanks to, I think, the method of, I think, Baujev of test function for elliptic inequalities and using different integral inequalities, we have the following results in the case of elliptic inequality. Under the assumption each PI's are greater than or equal to 1, if either of these two conditions are satisfied. That means in the case of 4, I think, if the summation of 1 over LI's, which is less than or equal to 1, the non-existence of this inequality should be ranged in Q, which is greater than or equal to the maximum of PI's. That means whenever the summation of 1 over Li is less than or equal to 1, so the inequality does not have any solution for any Q, which is greater than or equal to the maximum of PI's. Whereas in the case of the summation is of 1 over Li is greater than 1, the non-existence condition for Q is ranged in the form of this one. So inequality 1 does not have any non-trivial weak solution if either of these two conditions must be satisfied. The rough sketch of, I think, the proof of this result is sketched in the following one. So obviously, I think, as we know here, in the case of method of Baujev, we have to use the method of contradiction. For any Q which is greater than or equal to Pi, we have to assume that Q must be greater than or equal to each PI's, or it may be the maximum of PI's. By applying Young's inequality with different or appropriate parameters, we have to find, I think, from the weak formulation of the solution, we have to find, I think, these estimates or these integral inequalities. So in this case, our objective is to estimate the optimal a priori estimates of the right-hand sides of equation 6. So in order to find the optimal a priori estimates of the right-hand side, we have to introduce a standard cutoff function, that is test function, to estimate, I think, the right-hand side of this one. In this case, here C1 must represent, or it is a constant or some positive constants. So we have to define, or we have to introduce such standard cutoff function just like this, which is given by in the form of sum. I think psi of x is equal to here the product of psi of lambda 1, absolute value of x psi over r, the power of q minus pi over li for any x an element of r. In this case, lambda 1 should be estimated, or lambda 1 must be large enough so that the integral on the right-hand side of 6 should be defined and finite. That means in this particular case, lambda 1 must be the maximum of q over q minus pi's. And r is obviously, it is a positive real number, and this test function depends on r. And psi is a standard cutoff function which is satisfies, I think, the following relation. I think psi belongs to that class, and psi must be 1 whenever s is between 0 and 1. And if psi is greater than or equal to, it must be 0. And satisfies, I think, this condition. The value of psi at anywhere, I think, in between 1 and 2 must be in between 1 and 1. And for there exists some constant C2, so that the derivative must be in between of this one, or it may be decreasing. So using, I think, this 7 and 8, or the definition of the introduced cutoff function, I think 7 and 5, we have to estimate, I think, this integral, I think the integral of absolute value of u to the power of q times psi over the support of psi, is less than or equal to some constants times r to the power of q times minus 1 plus the summation of 1 over li minus the summation of pi over li's. So finally, we have found, I think, this right-hand side of equation number 1, these quantities. So because we are finding the non-existence condition for the inequality in the whole space, in the whole Euclidean space, we have to consider letting r goes to infinity. In equation number 9, we have the following two cases. So the first one is the integral over the whole R space, r to the power of n, is 0 whenever I think this q times the summation of 1 over li minus 1 less than the summation of pi over li. Whereas in the case of critical case, q times the summation of 1 over li minus 1 is equal to the summation of pi over li, I runs from 1 up to n. The integral of absolute value of u to the power of q over the whole Euclidean space r to the power of n is less than infinity. Now here to find, I think, the critical cases here, I mean, to find the condition of the non-existent condition, in the first case we have to consider, I think, the quantity in brackets. Whenever the quantity in brackets is 0 or less than or negative, q can take any value. But q must be greater than or equal to the pi's. In the case of critical condition, I think, using the method of Pahozhev, I think, we have to use Holder inequality. And finally, we have the integral of absolute value of u to the power of q dx is equal to 0 whenever, I think, the right-hand side, I think, here, this quantity or the critical case is equal to 0. That means this leads to a contradiction. This contradiction means u is identically 0. U is identically 0 because we start from here. There is some non-trivial solutions. So this leads to, I think, the assertion of the theorem. So some particular examples, I think, in this case, we have to consider here the anisotropic polyharmonic operators of this type, greater than or equal to this one. So where this anisotropic polyharmonic operator is defined in that form. So according to the theorem, I think here li and mi in this case it is twice of some ki's. Here I runs from 1 up to n. So in this case, I think the problem 2 or inequality 12 does not have a non-trivial solution if it's satisfied in this case. Whenever the total sum of 1 over ki is less than or equal to 2, it is q must be any value which is greater than or equal to pi's, all pi's. In the case of it is greater than 2, I think the q is ranged in that form. When we come to, I think, in the case of pi's, all of pi's are equal to p. All pi's are equal to p. And that summation must be greater than 1. So the non-existence condition for non-trivial solution of this inequality is reduced in the form of this type. Now here L bar stands for, I think, the harmonic mean of the li's, when if you consider L is a multi-index with coordinates L1, L2 up to Ln. So the non-existence condition of this inequality when pi's are p, it reduces in the form of this type. Next, I think the second one is a parabolic problem. The same operator with similar operator, of course, we have to use similar operator, but it is a backward parabolic problems in this case. So in the same thing like elliptic case, we have to introduce, I think, the admissible space of function of the solution in the form of this type. So in this case, I think we mean what we mean by, I think, this space, I think, LPI of the local of 0 t, LP local of r may be defined in the form of the space of all measurable function u in this set for any t that ranges between, I think, here 0 up to infinity. infinity, which satisfies, I think, that integral. So in this space, we have to find, I think, the non-existence condition of this solution of this problem as follows in this case. So we have to define, I think, here the weak solution of this type of parabolic, backward parabolic problem. First, we have to use the initial condition is locally integrable over the whole R to the power of n. So we have to consider a certain function u which belongs to this set. LQN intersection of that set is called a weak solution of this problem. For any non-negative test function, psi must belongs to this one, which satisfies, I think, this condition. So this is the weak formulation of, I think, the solution of this backward parabolic problem. So the second result, I think, in the case of backward parabolic problem, we have find this one under the condition here, pi is greater than 1, and q greater than the maximum of pi's. If condition 14 and condition 15 are satisfied, where omega of r satisfies this set, so the problem 2 does not have a global non-trivial weak solution in this case. So the proof of this one, again, here, similar to the elliptic case, we have to consider q greater than pi's, and q prime is the conjugate of q, that's q over q minus 1. So like elliptic case, we have to apply Young's inequality in the integrands of the problem, I think, here, there. So in the right-hand side of the integrand of the right-hand side, if you apply, I think, Young's inequality with appropriate parameter, we have to find, I think, this solution. I mean, this estimates. That means the integral of u naught of psi of x dx plus some constant b naught over 2 over the integral of absolute value of u to the power of q psi dx less than or equal to, I think, this right-hand side terms. Again, we have to find the optimal prior estimates of the right-hand side of equation 16, I mean, inequality 16. So in this case, we have to introduce a special cutoff function psi, which is defined, I think, from r to the power of n cross r plus into r plus. It is a non-negative test function, which is given by 17. So it is the product of this psi lambda of it, as stated in the case of elliptic case, times another in terms of components of time, t here, eta to the power of lambda 2 of t over r to the power of theta. So here lambda 1 and lambda 2 must be large enough so that the right-hand side of 16 must be defined and it's finite. So in this particular case, this lambda 1 and lambda 2 are calculated here. Lambda 1 must be greater than or equal to q over q minus pi. Lambda 2 is greater than q over q minus 1. Psi. So using this one, I think here we use this type of test function psi and eta may be defined which satisfies this condition. And we have to find, I think, in the estimates of 19. So in this case, just finding the optimal value of, I think, the right-hand side here. In the case of the implicit form, we have to find the solution, I think, the non-existence condition is 20. But in this case, I think finding the maximum of this one for theta greater than or equal to less than or equal to 0, it is the condition of non-existence of non-trivial solution is the finding of, I think, the value of theta greater than 0, the optimal value of theta. So from here, equation 20, I think, inequality 20 is equivalent to here 21. From 21, we have to find the optimal value of theta. And then finally, I think, like the case of elliptic case, will leads into a contradiction if the hypothesis of the theorem is satisfied. So like elliptic case, again, in the case of here, we have say types of condition is reduced when all pi is p, but it is still anisotropic. In the case of p1 is equal to 1 and k is equal to this one, I think this condition 22 is exactly or completely coincides with the condition of Fujit's type of non-existence of global solution to semi-linear parabolic inequalities. Like again here, we consider here a backward parabolic problem with anisotropic polyharmonic operators, just like that. So according to the theorem here, Ki Cni is equal to 2 Lis. So if these conditions are satisfied, then I think this 23, I think in problem 23 does not have non-trivial global solution, weak solution. And finally, I think I would like to just remark, I think, these general results. So the previous two, the elliptic inequality and the backward parabolic problem will be, were extended into a more general one by taking a more general anisotropic operators. Just here, the first is a general elliptic problem with an isotropic operator, and the second one, I think, here is a backward parabolic problem with general operator, with AI alpha, B beta I, F, G are carotidory function satisfying, I think, these conditions, this condition. So if this alpha I, A alpha I, B beta I, and G and F are satisfied this condition, then for any such another non-negative boundary function here, A alpha I and B beta I, we have, I think, also the non-existence results of these types of inequality and these types of problems. So I think the reference, I think, that I used here, this work, I think these references. And I think this is all about my talk. Thank you.
Thank you very much. Are there questions, comments?
Excuse me, what about optimality of this of your conditions? Do you have some examples of existence when you are at the border?
At this time, just I'm focusing on the existence of the solutions, of course. Of course, I didn't find maybe some examples for the critical case. I think we have to find maybe, of course, I will plan to find, I think, the critical case, to check the critical case, at the critical point, whether there is a non-trivial solution or not. So I think in this talk, I think I am focusing on only for the non-existence one.
I can answer you. In the sense of, by telling you a story, this is the end of the session. In Italy, we have a number of problems, actually. But we also have this problem that we have two eminent mathematicians. I will not say their names, but perhaps you can understand by the story. Two eminent mathematicians. One looks for existence of solutions. The other looks for non-existence results. And during a seminar, one of the two was the chairman, the other was the speaker. I don't remember. I don't remember who was for instance, the speaker was non-existence, and the chairman was in existence. He asked him, well, are those sharp? Can you get non-existence? Can you get existence results? That's that moment a terrible war was born, and still now we have this terrible problem among those two Italian mathematicians in Italy. And so, so sorry for telling you this story.